Hello there, and welcome to Just About Earth, a place where curiosity slows its breathing, where science is allowed to speak softly, and where complicated ideas are given time to unfold without pressure. Wherever you are right now, whatever kind of day you're easing out of, I'm glad you're here. Tonight, we're going to take our time with a question that sounds simple at first, but turns out to be anything but. It's a question about the human body, about history written not in books but in cells, sunlight and survival. It's a question about skin and how it came to look the way it does. Before we wander too far into that story, let me ask you something gently, the way one asks a question that doesn't demand an answer right away. Where are you listening from tonight? Is the light outside your window fading, or has it already gone? Maybe it's early morning where you are, or the middle of the afternoon, or one of those quiet in-between hours that don't quite belong to day or night. Wherever you happen to be on the planet, your body is carrying a history shaped by that place, and by many places before it. And whether you're fully awake, half dreaming, or simply resting your eyes, that history is still there, quietly doing its work. If you find this space calming, if you enjoy letting science unfold at an unhurried pace, you might consider liking the video or subscribing. It helps this small, quiet corner of the internet reach others who are looking for the same kind of gentle exploration. There's no rush though. For now, just settle in. Let your thoughts slow down. There's no test at the end, no conclusion you need to reach. We're just following a thread, one that begins far earlier than written history, far earlier than borders, flags, or names. Tonight's question is often phrased in a blunt way. Why did humans become white? It's a question that can sound uncomfortable, or even charged, depending on how it's asked and who's asking it. But when you strip away the assumptions, the politics, and the myths that have grown around skin colour, what remains is a deeply human story. Not a story of categories, but of adaptation. Not a story of superiority or hierarchy, but of bodies responding slowly and imperfectly to the world around them. To begin, it helps to pause and notice something that often goes unsaid. Human skin comes in an enormous range of shades, tones and textures, far more than the simple labels we tend to use. Even the word white is misleading. No one is truly white in the way paper is white, just as no one is truly black in the way night is black. These are rough descriptions we've inherited, not precise biological truths. Skin colour exists on a continuum, shaped by geography, ancestry and environment, blending gradually from darker to lighter as you move across the globe. Nature rarely draws sharp lines, even when human language tries to, but if we zoom out far enough, patterns do begin to appear. One of the most striking is the relationship between latitude and skin pigmentation. Populations whose ancestors lived for many thousands of years near the equator tend to have darker skin. Populations whose ancestors lived for long periods farther north or south tend to have lighter skin. This pattern isn't random, and it isn't cultural, it's biological, and it has everything to do with sunlight. To understand how this happened, we need to let go of the idea that skin colour was ever about appearance in the way we think of it today. For most of human existence, mirrors were rare or non-existent. There was no concept of beauty standards tied to pigmentation, no social media, no global comparisons. Skin colour mattered only insofar as it affected survival. It was part of the body's interface with the environment, like lungs responding to air or eyes responding to light. At its most basic level, skin colour is determined by a pigment called melanin. Melanin is produced by specialised cells in the skin and serves as a natural sunscreen. It absorbs ultraviolet radiation from the sun, protecting DNA from damage. The more melanin you have, the darker your skin appears, and the more protection you have against intense sunlight. This is not a cosmetic feature, it's a defensive one. Early humans evolved in Africa, in regions with strong direct sunlight throughout the year. In that environment, high levels of melanin were not just helpful, they were essential. Ultraviolet radiation can damage skin cells, increase the risk of skin cancer, and crucially, break down folate, a vitamin necessary for DNA synthesis and healthy reproduction. Folate deficiency can lead to serious birth defects. Darker skin helps protect folate levels by shielding the body from excessive UV exposure. In evolutionary terms, this protection translated directly into more surviving offspring. So for a very long time, human skin was dark. Not because it had to be, but because it worked. It was a solution to a specific set of conditions. And as long as humans stayed in environments with strong sunlight, there was no pressure to change that solution. Evolution, contrary to popular belief, doesn't seek improvement in any abstract sense. It favours what works well enough right now under current conditions. But humans are a restless species. At some point, groups of humans began to move out of Africa, travelling into regions with different climates, different landscapes, and very different relationships to the sun. As they moved northward into Europe and parts of Asia, the intensity of sunlight dropped. Days grew shorter in winter. Clouds, snow, and lower sun angles reduced the amount of ultraviolet radiation reaching the ground. The same skin that had been protective near the equator now created a new challenge. Here's where the story becomes less intuitive. Sunlight, especially ultraviolet B radiation, isn't just something the body needs to defend against. It's also something the body uses. When UVB rays hit the skin, they trigger the production of vitamin D, a substance essential for calcium absorption, bone health, immune function, and many other processes. Without enough vitamin D, bones can become soft or malformed, a condition known historically as rickets. In severe cases, it can affect pelvic shape, making childbirth more dangerous, and it can weaken the immune system. In regions with low sunlight, having too much melanin becomes a disadvantage. Darker skin blocks UVB rays more effectively, which means less vitamin D production. In environments where UVB is already scarce, this can lead to chronic deficiency. Over many generations, individuals whose skin allowed more UVB to penetrate had a slight survival advantage. Their bones were stronger, their immune systems functioned better, their children were more likely to survive. It's important to emphasize how slow and subtle this process was. No one woke up one day lighter-skinned. There was no sudden shift, no moment where humans became white. Instead, small genetic variations affected how much melanin was produced, how it was distributed in the skin, and how responsive melanocytes were to sunlight. In low UV environments, variants that reduced melanin slightly became more common over time, simply because they worked better under those conditions. This process didn't happen once, in one place. It happened independently in different populations. The genetic pathways that led to lighter skin in Europe are not identical to those that led to lighter skin in East Asia. This is a crucial point that often gets overlooked. Light skin is not a single trait with a single origin. It's a convergent outcome reached by different routes in response to similar environmental pressures. In other words, lighter skin didn't spread because it was inherently better. It spread because it solved a specific problem in specific places. And where that problem didn't exist, darker skin remained advantageous. Even today, the distribution of skin pigmentation across the globe reflects this balance between UV protection and vitamin D production. What makes this story particularly interesting is that it challenges many assumptions people carry, often without realizing it. There's a persistent myth that lighter skin is somehow more advanced or more recent in a linear sense. In reality, all human populations are equally modern. No group stopped evolving while another continued. Skin pigmentation changed because environments changed, not because of progress in any moral or intellectual sense. It's also worth noting that the environments humans lived in continued to shift. Diets changed with the advent of agriculture. Clothing reduced sun exposure. Shelters altered daily light patterns. These cultural factors interacted with biology, sometimes reinforcing existing trends, sometimes complicating them. Evolution doesn't stop when culture begins. The two are always intertwined. As you sit or lie there now, your own skin is performing the same basic functions it always has. It's regulating temperature, providing a barrier, responding to light. It's carrying traces of journeys taken by people you'll never meet, across landscapes that may no longer look the same. And it's doing all of this without commentary, without awareness, simply because chemistry and biology found ways to make it work. This is where the question starts to open outward rather than close in. When we ask why humans became lighter-skinned in some regions, we're really asking how flexible the human body is, how deeply connected it is to place, and how much of what we think of as identity is actually adaptation. The answer isn't found in labels or categories, but in trade-offs, constraints, and quiet adjustments made over thousands of years. For now, though, it's enough to rest with the idea that skin colour, in all its variation, is not a message or a ranking. It's a record, a quiet one, written slowly. And as we follow that record further back and further outward, the story becomes less about white or dark, and more about what it has always been about. Humans moving through light. Long before borders, before languages split and names took hold, before there were questions about difference at all, there were people living beneath a sun that was both generous and unforgiving. This was the setting in which our species took shape, not in fragments or isolated pockets, but as a continuous population adapting day by day to a powerful environment. To understand why human skin looks the way it does today, it's necessary to spend some time here, in this place of origin, because nothing about later changes makes sense without first understanding the conditions that shaped the beginning. Africa, especially the regions near the equator, receives some of the most intense and consistent sunlight on Earth. The sun there is high in the sky for much of the year, its rays travelling a short direct path through the atmosphere before reaching the ground. This means higher levels of ultraviolet radiation, particularly UVB and UVA, striking the skin. For early humans who lived outdoors nearly all the time, this was not an occasional exposure. It was constant. Hunting, gathering, walking, resting, socialising, raising children, all of it happened under open skies. Shade existed, but it was not a permanent refuge. Clothing, as we understand it today, was minimal or non-existent for much of this period. Skin was exposed, regularly, and for long stretches of time. In that context, skin was not simply a covering. It was an active organ, deeply involved in survival. One of its most critical roles was protecting the body from the harmful effects of ultraviolet radiation. UV exposure can damage DNA, increasing mutation rates in skin cells. While mutations are part of evolution, uncontrolled damage can be fatal or reduce reproductive success. More subtly, UV radiation breaks down folate, a B vitamin essential for cell division and fetal development. Folate deficiency during pregnancy can lead to severe neural tube defects. In populations exposed to intense sunlight year-round, preserving folate levels was not optional, it was essential. This is where melanin becomes central to the story. Melanin is a pigment produced by specialized cells called melanocytes. It absorbs and scatters ultraviolet radiation, reducing how deeply it penetrates the skin. The more melanin present, the darker the skin appears, and the greater the protection against UV damage. Importantly, the number of melanocytes does not vary dramatically between people. What varies is how much melanin they produce and how it is packaged and distributed within skin cells. In high UV environments, natural selection favoured individuals whose skin produced larger amounts of melanin, forming a protective barrier against the sun's intensity. Over many generations, this pressure shaped early human populations. Darker skin was not a cosmetic trait or a social signal. It was a functional adaptation. Individuals with higher melanin levels were more likely to maintain healthy folate levels, experience less UV-induced damage, and successfully reproduce. Their children inherited similar traits, and over time, these traits became common. This is not a story of intention or design. No one chose darker skin. It emerged because, in that environment, it worked. It's worth pausing to recognise how long this period lasted. Anatomically, modern humans evolved in Africa roughly 200,000 to 300,000 years ago. For tens of thousands of years, all humans lived in similar high UV environments. During that time, dark skin was the norm. There was no variation toward lighter skin, because there was no advantage to it. Evolution does not anticipate future migrations. It responds to present conditions. As long as those conditions remained stable, so did the traits shaped by them. This also means that dark skin is not a specialized or derived feature in human history. It is the ancestral condition. It represents the baseline from which later variations emerged. Every genetic change associated with lighter skin occurred after humans began moving into regions with lower UV exposure. In that sense, darker skin is not something humans became. It is something humans began with. The African environment shaped more than pigmentation. It influenced body proportions, sweating mechanisms, hair texture, and metabolism. But skin color is particularly revealing because of how directly it interacts with sunlight. Early humans evolved an efficient sweating system that allowed them to cool their bodies during prolonged activity in hot climates. Hair on the body became finer and sparser, improving heat dissipation. This increased skin exposure, which in turn increased UV exposure, reinforcing the importance of melanin as protection. These traits work together as part of an integrated system for surviving and thriving under an intense sun. Life in these environments required mobility. Early humans were endurance walkers and runners, covering long distances in search of food and water. This meant hours spent in open landscapes like savannas and woodlands, where shade could be limited. The ability to remain active without overheating was a major advantage, but it came at the cost of greater sun exposure. Again, melanin helped mitigate that cost. It's also important to understand that Africa itself is not uniform. It contains deserts, rainforests, highlands, coastlines, and everything in between. Sunlight intensity varies with altitude, cloud cover, and geography. As a result, there was variation in skin tone even within Africa, though it remained within a darker range overall. Human populations have never been genetically identical. There has always been diversity. What matters is the direction of selective pressure. In Africa, that pressure consistently favoured protection from UV radiation. Because this period sits so far back in time, it can feel abstract, like a prelude that doesn't quite connect to the present. But the genetic foundations laid here persist in every human alive today. The machinery for producing melanin, responding to sunlight and regulating pigmentation is shared across all populations. Later changes did not replace this system. They modified it. The default state of human skin remains capable of producing significant melanin when exposed to UV radiation. This is why people with ancestries from low UV regions can still tan, sometimes deeply, when exposed to strong sunlight. The ancestral response is still there. Another point that often gets overlooked is how little visual variation would have mattered socially at this stage. Early human groups were small. People lived in bands of related individuals who shared similar appearances. There was no global comparison, no concept of us and them based on skin colour. Differences that did exist were gradual and local, not categorical. Skin colour had no symbolic meaning. It was not identity, it was function. This matters because many modern misunderstandings come from projecting current social meanings backward onto deep history. When we imagine early humans, it's tempting to picture them through modern lenses, assigning categories that didn't exist. But the reality was much simpler. People lived where they lived. Their bodies responded to those places. That was the entire process. As generations passed, small genetic variations continued to arise through mutation. Some affected pigmentation slightly, making skin marginally darker or lighter. In Africa's intense sunlight, variations toward lighter skin offered no advantage, and sometimes posed risks. Those variations did not spread widely. They remained rare or disappeared. Variations toward darker pigmentation, on the other hand, were neutral or beneficial and could persist. Over long periods, this maintained a population-level pattern. This is a good place to clarify what evolution does and does not do. Evolution does not optimize for perfection. It doesn't create the best possible organism. It favors traits that increase reproductive success under specific conditions. If conditions change, the direction of selection can change. If they remain stable, traits can remain stable for very long periods. The African sun provided a remarkably consistent selective environment over much of human evolutionary history. Eventually, though, that stability would be disrupted. Some human groups began moving beyond Africa, following coastlines, river valleys, and animal migrations. These movements were not planned expeditions. They were gradual expansions happening over thousands of years. People moved into new environments without knowing what challenges lay ahead. Their bodies, shaped by one kind of sunlight, would encounter another. But before that story unfolds, it's worth lingering a little longer with the idea that human diversity did not begin with difference between continents. It began with a shared origin. Every variation we see today emerged from populations that once lived under similar skies, facing similar pressures, responding to the same sun. If you imagine those early humans resting at the end of a day, bodies tired from movement, skin warmed by sunlight, there is no hint of the meanings that would later be layered onto pigmentation. There is no hierarchy, no symbolism. There is just biology doing what biology always does, responding to the world as it is. Skin is often treated as something passive, a surface we decorate, protect from the cold, or worry about aesthetically. But for most of human history, skin was one of the body's most important tools for staying alive. It was not just a boundary between the inside and the outside. It was an active interface with the environment, constantly responding to heat, light, injury, and infection. And when it came to sunlight, skin was not merely exposed to it, it negotiated with it. At the center of that negotiation is melanin. Melanin is a complex group of pigments produced inside specialized cells called melanocytes, which are found in the bottom layer of the epidermis. These cells manufacture melanin within small packages called melanosomes, and then distribute those packages to surrounding skin cells. Once there, melanin forms a kind of microscopic umbrella over the cell's nucleus, absorbing and scattering ultraviolet radiation before it can damage DNA. This arrangement is not accidental. It is the result of countless generations in which even small improvements in protection made a difference. What's important to understand is that melanin is not a simple on-off switch. It exists in different forms, primarily eumelanin, which is brown to black, and pheomelanin, which is red to yellow. The ratio of these types, along with how much is produced and how it is distributed, influences skin tone. Most people around the world produce some combination of both, but populations whose ancestors lived in high UV environments tend to produce more eumelanin, which is more effective at blocking ultraviolet radiation. Ultraviolet radiation itself comes in several forms, but the two most relevant here are UVA and UVB. UVA penetrates deeper into the skin and contributes to aging and indirect DNA damage. UVB is more energetic and directly damages DNA, but it's also the wavelength responsible for triggering vitamin D production. In environments with intense sunlight, UVB levels are high enough that vitamin D production is rarely a problem, even with high melanin levels. The risk lies in the damage UV can cause, particularly to folate. Folate, also known as vitamin B9, plays a crucial role in DNA synthesis and repair. It is especially important during pregnancy, when cells are dividing rapidly. UV radiation can break down folate circulating in the bloodstream. In regions with strong sunlight, this breakdown can happen quickly. Low folate levels are associated with serious reproductive consequences, including neural tube defects in developing embryos. From an evolutionary perspective, Anything that increases the likelihood of healthy reproduction becomes enormously important. This is where dark pigmentation becomes a matter of survival rather than appearance. Higher melanin levels reduce UV penetration, preserving folate and protecting DNA. Individuals with darker skin in high UV environments were more likely to produce healthy offspring who inherited similar pigmentation traits. Over many generations, this created a strong correlation between intense sunlight and darker skin. It's easy to imagine this process as neat and linear, but in reality it was messy and gradual. Mutations that slightly altered melanin production arose randomly. Some made skin marginally darker, others marginally lighter. In Africa's sun-rich environments, mutations toward darker pigmentation were either beneficial or neutral. Mutations toward lighter pigmentation offered no advantage and sometimes carried hidden costs. As a result, darker variants tended to persist and spread, while lighter ones did not. This selective pressure operated quietly. There was no visible moment where melanin won. It simply became common because it worked. And because the environment remained relatively stable for long stretches of time, the pressure remained consistent. This allowed dark pigmentation to become deeply established as the ancestral human condition. Another factor that often goes unnoticed is how early human lifestyles amplified sun exposure. Humans are unusual among mammals in their reliance on sweating to regulate body temperature. Sweating is highly effective for cooling, but it requires relatively hairless skin. As humans lost most of their body hair, more skin was directly exposed to sunlight. This increased the importance of pigmentation as protection. In other mammals with dense fur, hair itself blocks a significant amount of UV radiation. Humans, by contrast, relied on skin pigmentation to fill that role. Movement also mattered. Early humans were endurance foragers and hunters. They travelled long distances on foot, often during the heat of the day. This behaviour increased cumulative UV exposure. A person who spends hours each day walking or running under open skies experiences a very different UV load than someone who remains mostly shaded. Over a lifetime, and across generations, those differences add up. It's also worth noting that skin cancer, while dangerous, is not the primary evolutionary driver here. Most skin cancers develop later in life, often after reproductive age. While severe cases can affect survival earlier, the more significant pressure likely came from folate preservation and overall cellular integrity. Evolution tends to favour traits that protect reproduction, even if they do not eliminate all long-term risks. The protective role of melanin extends beyond UV radiation. Melanin has antioxidant properties and may help protect against certain pathogens. Skin is the first line of defense against the outside world, and pigmentation can influence how that defense operates. While UV protection is the most well-studied function, melanin's role in immune response and inflammation is still being explored. What's clear is that pigmentation is not a superficial trait. It is integrated into broader physiological systems. One misconception that often arises is the idea that darker skin is somehow more primitive or less refined. This belief has no basis in biology. Producing melanin is metabolically expensive. It requires energy and resources. The body does not maintain such a system without reason. In environments where melanin is beneficial, investing in it makes sense. In environments where it is less beneficial or even costly, natural selection can favour reduced production. Neither outcome is inherently better. Each is context dependent. The language of shield is useful here, but it should not be taken too literally. Melanin does not block all UV radiation. It reduces exposure to safer levels. Even very dark skin allows some UVB penetration, which is why vitamin D production is still possible near the equator. The system is calibrated, not absolute. It represents a compromise shaped by long-term averages rather than short-term extremes. This idea of compromise is central to understanding human skin variation. Every trait involves trade-offs. Too little melanin in a high UV environment increases the risk of folate degradation and DNA damage. Too much melanin in a low UV environment reduces vitamin D synthesis. Evolution does not aim for a single optimal state. It adjusts traits toward local balances. For a very long time, the balance point for humans was firmly on the side of protection. The African sun demanded it. And because humans remained in similar latitudes for tens of thousands of years, there was no pressure to explore other balances. Skin colour remained relatively stable across generations, with variation constrained within functional limits. This stability is part of why the later emergence of lighter skin can seem puzzling. If dark skin worked so well, why change it at all? The answer lies not in any flaw in melanin, but in the changing relationship between humans and sunlight as people moved away from the equator. When UV levels drop low enough, the protective shield becomes less necessary and its costs become more visible. But that shift did not happen immediately. Early migrations out of Africa followed routes that stayed close to the sun, such as coastal paths. It took time and many generations before populations found themselves living in places where UV scarcity was a serious issue. During that time, the ancestral pigmentation system remained largely intact. It's also important to remember that evolution works on populations, not individuals. A single person with lighter skin in a high UV environment does not change the trajectory of a population. What matters is whether that trait consistently leads to more surviving offspring over many generations. In Africa it did not, so the system stayed as it was. As you consider this, it may help to step away from modern categories entirely. Early humans did not think of themselves as dark or light. They thought in terms of kin, territory, food, and survival. Skin colour was not an identity. It was not noticed in the way we notice it now. It was simply part of the body, like height or hand shape, shaped by forces no one could see. The shield metaphor also invites us to think about vulnerability. A shield implies a threat. In this case, the threat was not the sun itself, but imbalance. Too much radiation, too little protection, and the body suffers. Too much protection in the wrong place, and other systems struggle. Melanin sits at that intersection, adjusting exposure rather than eliminating it. This adjustment was not conscious. There was no awareness of UV wavelengths or vitamins. There were only outcomes: healthier children, stronger bodies, higher chances of surviving infancy. Over time, those outcomes shaped the genetic landscape. As humans began to move into new environments, this balance would be tested in new ways. The shield that once offered clear advantages would begin to interfere with other needs. The story of skin colour would shift from one of protection to one of compromise under changing light. But even then, melanin would not disappear. It would be recalibrated, not abandoned. For now, it's enough to recognise that skin pigmentation began as a solution to a specific and serious problem. It was not random. It was not symbolic. It was survival chemistry playing out over deep time. Every variation that followed grew out of this foundation, shaped by the same basic logic, even as conditions changed. For most of human existence, the world ended where familiar landscapes gave way to uncertainty. Rivers marked edges, deserts discouraged movement, dense forests slowed travel. Yet over time, small groups of humans did something remarkable. They kept going. Not all at once, not with maps or plans, but step by step, generation by generation, following food, water, animals, and seasons. This gradual movement carried humans out of the tropics and into environments where the sun behaved differently, where light arrived at an angle, where days shortened and lengthened dramatically over the year, and where the rules the body had quietly relied on for thousands of years began to shift. Leaving the tropics was not a single event. It was not a great migration with a clear starting line and finish. It was a slow dispersal, unfolding over tens of thousands of years. Some groups moved along coastlines, where food was reliable and temperatures were moderated by the sea. Others followed river systems inland. Some paused for long periods, settling into new regions, while others continued onward. At no point did anyone know they were embarking on a journey that would eventually reshape human biology. They were simply responding to immediate needs. As humans moved northward and southward away from the equator, one of the most significant changes they encountered was light. Near the equator, daylight length varies little across the year. The sun rises and sets at roughly the same times, and it climbs high overhead each day. Ultraviolet radiation is abundant and consistent. But farther from the equator, sunlight becomes seasonal. In winter, days grow short. The sun stays low in the sky, and its rays pass through more atmosphere before reaching the ground. This filters out a substantial portion of UVB radiation. At first, these differences may not have been dramatic enough to matter. Early migrations stayed mostly within subtropical regions where sunlight was still relatively strong. The ancestral balance between melanin and vitamin D production held. But as populations gradually settled at higher latitudes, particularly in parts of Europe and northern Asia, the cumulative effects of reduced UV exposure began to emerge. To appreciate how subtle these changes were, it helps to think in terms of averages rather than extremes. A single cloudy day means little. A long winter matters more. A lifetime spent in a low UV environment matters most of all. Evolution responds to these long-term patterns, not to short-term fluctuations. Over many generations, small differences in sunlight exposure translated into differences in health, fertility, and survival. One of the key challenges in these new environments was vitamin D. Unlike many nutrients, vitamin D is not readily available in most plant-based foods. It can be obtained from certain animal products, especially fatty fish and liver, but for much of human history, the primary source was synthesis in the skin triggered by UVB radiation. In regions where UVB was limited for large parts of the year, relying on sunlight alone became less reliable. For people whose ancestors had evolved under intense tropical sun, high melanin levels were the norm. That pigmentation continued to block UVB efficiently, even when UVB was scarce. This meant that in higher latitudes, individuals with darker skin could struggle to produce enough vitamin D, particularly during long winters. Vitamin D deficiency does not usually kill quickly. Instead, it weakens bones, compromises immune function, and increases the risk of complications during pregnancy and childbirth. These effects may be subtle in individuals, but across populations and generations, they can influence reproductive success. At this point, the protective shield of melanin began to present a trade-off. What had once been clearly beneficial now carried a cost. In environments with weak sunlight, allowing more UVB to penetrate the skin became advantageous. This set the stage for a gradual shift in pigmentation. It's important to stress that this shift did not happen immediately upon leaving the tropics. For long periods, human populations lived in intermediate environments where the balance was still workable. Clothing, shelter, and diet also played roles. The use of animal skins and later woven fabrics reduced sun exposure further, potentially increasing vitamin D challenges. Fire allowed people to cook food, altering nutrient availability. Diets rich in fish or animal fat could partially compensate for reduced sunlight, reducing selective pressure on skin pigmentation. These interacting factors meant that changes in skin colour were neither uniform nor inevitable. Different populations experienced different pressures depending on latitude, climate, diet, and lifestyle. This is why human skin variation today does not form neat bands or categories. It reflects a patchwork of adaptations to local conditions. Another aspect of leaving the tropics that often goes overlooked is how dramatically seasons change daily life. In higher latitudes, winter brought not just cold, but darkness. Long nights meant fewer daylight hours for activity. Sunlight became a limited resource rather than a constant presence. This altered how bodies interacted with light at every level, from circadian rhythms to vitamin synthesis. Children growing up in these environments experience different developmental conditions than their ancestors. Their bones formed under different nutritional constraints. Their immune systems faced new pathogens. Their bodies adapted to cold as well as darkness. Skin pigmentation was only one piece of a broader suite of changes, but it was a visible one. As generations passed, genetic variations that slightly reduced melanin production became more relevant. In the tropics, such variations had offered no benefit. In higher latitudes, they allowed more UVB penetration and more reliable vitamin D synthesis. Individuals with these traits were, on average, healthier and more likely to reproduce successfully. Over many generations, these traits became more common. Crucially, this process did not require skin to become very light all at once. Even small reductions in melanin could make a difference. Over time, these small shifts accumulated. Skin tones lightened gradually, often unevenly, and not in the same way everywhere. This is why it is misleading to speak of humans becoming white, as if it were a single event. What happened instead was a series of localized adjustments, each responding to a specific light environment. In some regions, skin became lighter relatively quickly. In others, it remained darker or intermediate. In still others, populations moved back and forth between latitudes, mixing genetic traits and blurring patterns. Another factor complicating this picture is that migration did not always move in one direction. Humans did not simply leave Africa and fan out permanently. There were multiple waves of movement, periods of isolation, and later periods of contact and mixing. Populations that had adapted to lower UV environments sometimes moved back toward higher UV regions, bringing lighter skin traits with them. In those contexts, the balance shifted again, and selective pressures changed. Throughout all of this, evolution remained indifferent to human categories. It did not care about colour in any symbolic sense. It responded to light levels, nutrient availability, and reproductive outcomes. The same logic applied everywhere, even as the details differed. One way to understand this process is to think of skin pigmentation as a dial rather than a switch. The dial is turned up or down depending on environmental conditions. In the tropics, it is turned up to provide protection. Farther from the equator, it is turned down to allow absorption. The dial can be set to many positions, and it does not need to reach an extreme to be effective. As humans continued to spread into northern Europe, Siberia, and eventually the Americas, some populations found themselves in environments with very low UV levels for much of the year. In these places, the pressure toward lighter skin became stronger, but even there, the outcome was shaped by diet and culture. Groups with diets rich in vitamin D, such as Arctic populations consuming marine mammals and fish, retained relatively darker skin despite high latitudes. Their nutritional intake reduced the need for increased UV absorption. This point is particularly important because it underscores that skin colour is not determined by latitude alone. It emerges from the interaction of sunlight, diet, behaviour, and genetics. Simplistic explanations miss this complexity and often lead to incorrect assumptions. As humans journeyed into new light, they did not leave their biology behind. They carried it with them, adjusting it slowly as conditions demanded. These adjustments were not visible to those living through them. No one noticed their skin becoming slightly lighter over generations. No one attributed meaning to these changes. They were simply part of the background of life. From our perspective, looking back across tens of thousands of years, the pattern becomes clearer. We can trace genetic changes, map migration routes, and correlate pigmentation with latitude. But it's important to remember that this clarity is retrospective. For the people living these lives, the world was immediate and practical. Survival came first, biology followed, and yet, even as skin lightens in some populations, the underlying system remains the same. Melanin is still produced. Skin still responds to sunlight. The shield is adjusted, not discarded. The journey into new light does not erase the past. It layers new adaptations onto an ancient foundation, carrying the history of human movement quietly within the skin itself as the path continues onward. As human groups settled farther from the equator, something subtle but profound began to shape everyday life. The sun, once a constant presence overhead, no longer dominated the sky in the same way. It still rose and set, of course, but its path was lower, its warmth less direct, its influence uneven across the year. In these northern regions, sunlight became something you noticed not because it was overwhelming, but because it could be absent for long stretches of time. Days shortened in winter. Shadows stretched. The body, which had evolved for generations under reliable light, now had to function under conditions of scarcity. Living in northern latitudes meant adjusting to extremes that earlier humans had never faced. Summers could be bright and long, sometimes with light lingering late into the evening, but winters brought prolonged darkness. In some regions, daylight dwindled to just a few hours, with the sun barely lifting above the horizon. Even when it did appear, its rays travelled at a shallow angle, passing through more of the Earth's atmosphere, which filtered out much of the ultraviolet radiation. For the human body, this was not just a change in scenery. It was a fundamental shift in the availability of a critical environmental input. Ultraviolet B radiation, the portion of sunlight responsible for triggering vitamin D production in the skin, decreases dramatically with latitude. Above roughly 37 degrees north or south, UVB levels during winter months drop so low that vitamin D synthesis becomes negligible, regardless of how long you stay outside. In these regions, the body must rely on vitamin D stored from sunnier months, or obtained through diet. For populations whose ancestors had spent hundreds of thousands of years in sun-rich environments, this posed a new and persistent challenge. The effects of vitamin D deficiency are not always immediate or dramatic. They unfold slowly, often invisibly, but their consequences can be serious. In children, insufficient vitamin D can lead to rickets, a condition characterized by soft, weak bones that may bend or fracture easily. In adults, it can cause osteomalacia, leading to bone pain and muscle weakness. Beyond the skeleton, vitamin D plays a role in immune function, inflammation regulation, and muscle performance. Chronic deficiency can increase susceptibility to infections and complicate pregnancy and childbirth. In northern environments, these risks were not evenly distributed. Individuals with skin that allowed more UVB penetration could synthesize vitamin D more efficiently during the limited periods when sunlight was available. Those with higher melanin levels, which had been protective in the tropics, now faced a disadvantage. Their skin continued to block UVB effectively, even when UVB was scarce. Over time, this imbalance could influence overall health and reproductive success. The key here is not that darker skin suddenly became harmful. Rather, the cost-benefit balance shifted. In low UV environments, the protective benefit of high melanin diminished, while its cost in terms of reduced vitamin D production became more significant. Evolution responds to these kinds of trade-offs, but it does so slowly, through small changes accumulating over many generations. Northern latitudes also brought new environmental stresses beyond light alone. Cold temperatures placed additional demands on metabolism. Energy expenditure increased as bodies worked to maintain warmth. Diets shifted toward higher reliance on animal fat and protein, which provided calories and, in some cases, vitamin D. Clothing became more substantial, reducing skin exposure to sunlight even further. Shelters enclosed people indoors for longer periods, especially during winter. Each of these factors interacted with skin pigmentation in complex ways. Clothing in particular is an often underestimated influence. In tropical environments, minimal clothing meant extensive skin exposure, reinforcing the importance of pigmentation as protection. In colder climates, layers of animal skins and later textiles covered much of the body year-round. This reduced UV exposure regardless of skin tone, intensifying the challenge of vitamin D synthesis. Under these conditions, any genetic variation that allowed more efficient UV absorption through exposed areas such as the face and hands, could provide an advantage. It's important to remember that the human body does not respond to averages alone, it responds to critical periods. For vitamin D, pregnancy and early childhood are especially important. Deficiencies during these stages can have long-term effects on skeletal development and reproductive anatomy. In populations living under low UV conditions for many generations, even small improvements in vitamin D availability during these windows could influence survival and fertility rates. This is how selective pressure operates quietly. There is no dramatic turning point, no moment where a population suddenly changes. Instead, individuals with certain traits have slightly better outcomes. Their children survive at marginally higher rates. Over time, these differences shape the genetic makeup of the population. As humans adapted to northern latitudes, skin pigmentation became part of a broader suite of physiological adjustments. Body proportions changed, with shorter limbs and more compact builds helping conserve heat. Fat distribution shifted. Metabolic rates adapted. These changes did not occur in isolation. They interacted with one another, reflecting the complex demands of colder, darker environments. In this context, lighter skin pigmentation emerged as one component of a larger adaptive pattern. Reduced melanin production allowed more UVB penetration during the limited periods of sunlight, supporting vitamin D synthesis. This did not require skin to become extremely light. Even modest reductions could make a meaningful difference. Over time, however, in regions with very low UV availability, stronger selective pressure pushed pigmentation further along that gradient. It's crucial to emphasize that these changes were not uniform across all northern populations. Geography mattered. Coastal groups often had access to vitamin D-rich foods such as fish and marine mammals. This dietary intake could offset low UV exposure, reducing the selective pressure for lighter skin. As a result, some high-latitude populations retained relatively darker pigmentation, despite living far from the equator. In contrast, inland populations with diets low in vitamin D face stronger pressure to adapt through skin pigmentation. This is one reason why skin colour patterns do not align perfectly with latitude. They reflect a combination of sunlight, diet, cultural practices, and genetic history. Seasonality also shaped how the body interacted with light. In northern regions, vitamin D synthesis was often confined to a narrow window during late spring and summer. During these months, efficient absorption and storage became crucial. Lighter skin allowed more rapid vitamin D production when UVB was available, helping build reserves to last through the winter. Darker skin slowed this process, increasing the risk of deficiency. This seasonal bottleneck highlights how timing matters in evolution. Traits that improve performance during critical periods can have outsized effects on survival. In this case, the ability to quickly synthesize vitamin D during short summers could influence health outcomes months later, during pregnancy or early childhood in winter. As generations passed, the cumulative effect of these pressures became visible in skin tone. Populations in northern Europe and parts of Asia gradually developed lighter pigmentation. Genetic studies show that multiple genes are involved in this process, each contributing a small effect. These genes influence melanin production, distribution, and response to sunlight. Importantly, different populations arrived at lighter skin through different genetic pathways, reinforcing the idea that this was not a single event, but a repeated solution to a shared problem. The phrase, "the sun grows distant," captures more than just physical distance. It reflects a changing relationship between humans and their environment. Sunlight, once abundant and potentially dangerous, became limited and necessary. The body's priorities shifted accordingly. Protection gave way to absorption, not because one was better than the other, but because conditions demanded it. Throughout this process, there was no awareness of what was happening. People did not notice gradual changes in skin tone across generations. They did not associate those changes with health or survival. Life was immediate, shaped by hunting success, shelter, community, and weather. Evolution worked in the background, adjusting traits without commentary. From a modern perspective, it can be tempting to view lighter skin as an endpoint, as if evolution were aiming toward it. This is a misunderstanding. Lighter skin is not an ultimate form. It is a local adaptation, useful in some environments and less so in others. In fact, in today's globalized world, where people move rapidly between latitudes and lifestyles change faster than biology can follow, these adaptations can become mismatched with environment, leading to new health challenges. But in the context of early human history, these changes made sense. They reflected a body trying to maintain balance under new constraints. The sun did not disappear, but it became less reliable. Skin responded accordingly. Long before anyone knew its name, long before laboratories or vitamins bottled in amber glass, vitamin D was already exerting a quiet influence over human lives. It worked invisibly, without sensation, without warning signs until something went wrong. No pain announced its absence at first. No immediate signal told the body it was running low. And yet, over time, its presence or absence shaped bones, altered immune defences, affected fertility, and quietly guided which traits were passed on to the next generation. In places where sunlight was abundant, vitamin D flowed easily into human biology. In places where light grew scarce, it became a limiting factor, exerting pressure that was slow, persistent, and deeply consequential. Vitamin D is unusual among nutrients. Unlike most vitamins, it is not primarily obtained from food. Instead, it is synthesized in the skin when ultraviolet B radiation interacts with a cholesterol-derived molecule. This process turns an inactive precursor into vitamin D3, which is then modified by the liver and kidneys into its active form. The entire pathway depends on UVB light. Without sufficient exposure, the process slows or stops, regardless of how healthy the rest of the body may be. In tropical regions, this system functions with little difficulty. UVB radiation is strong and consistent throughout the year. Even with high levels of melanin blocking a significant portion of incoming UVB, enough light penetrates the skin to maintain adequate vitamin D levels. For early humans living under these conditions, vitamin D deficiency was unlikely. The sun delivered more than enough input to keep the system running smoothly. As humans moved into higher latitudes, this reliability disappeared. The angle of the sun lowered, UVB radiation weakened. During winter months, it vanished almost entirely. In these environments, the body's ability to produce vitamin D depended on narrow windows of opportunity, sometimes only a few months long. Any factor that reduced UVB penetration during those periods could have lasting effects. Melanin, which had served as a protective filter in the tropics, now interfered with vitamin D synthesis. By absorbing and scattering UVB radiation, melanin reduced the amount of light reaching the deeper layers of the skin where vitamin D production begins. In high UV environments, this reduction was insignificant. In low UV environments, it became critical. The consequences of vitamin D deficiency unfold slowly. One of its most important roles is regulating calcium and phosphate metabolism, which are essential for bone formation and maintenance. Without sufficient vitamin D, calcium absorption from the gut decreases. The body compensates by drawing calcium from bones, weakening them over time. In children, whose bones are still growing, this can lead to rickets, a condition characterized by soft, pliable bones that bend under the body's weight. In adults, it leads to osteomalacia, marked by bone pain and muscle weakness. These skeletal effects are not merely cosmetic or uncomfortable, they can be life-altering. Deformed pelvises increase the risk of obstructed labour, making childbirth more dangerous. Fragile bones increase the likelihood of fractures, which in prehistoric environments could be fatal or severely limiting. Muscle weakness reduces mobility and endurance, compromising the ability to hunt, gather or escape danger. Beyond the skeleton, vitamin D influences immune function. It plays a role in regulating inflammatory responses and supporting the body's defense against pathogens. Chronic deficiency can increase susceptibility to infections which, in environments without modern medicine, posed a constant threat. Illness that might be manageable today could have been deadly in the past, particularly for infants and pregnant individuals. All of this means that vitamin D availability was not a minor concern. It affected survival, reproduction, and the health of future generations. In environments where sunlight was limited, any trait that improved vitamin D synthesis, even slightly, could influence evolutionary outcomes. This is where the concept of invisible pressure becomes important. No one could see vitamin D levels. No one could feel them dropping day by day. The pressure it exerted was statistical rather than dramatic. Individuals with better vitamin D status were, on average, healthier. Their children were, on average, more likely to survive. Over many generations, these small advantages accumulated, shaping populations in subtle but persistent ways. Skin pigmentation became part of this equation because it directly affected how much UVB reached the skin's vitamin D-producing machinery. Individuals with slightly lower melanin levels could synthesize vitamin D more efficiently during limited sunlight periods. This did not make them immune to deficiency, but it reduced the risk. Over time, in low UV environments, such traits became more common. It's important to emphasize that this process did not require extreme changes. Even modest reductions in pigmentation could improve vitamin D synthesis enough to matter. Evolution works on gradients, not absolutes. Skin did not need to become pale overnight. It lightened gradually, responding to long-term averages rather than short-term extremes. Diet played a role as well, complicating the picture. Certain foods contain vitamin D, particularly fatty fish, fish liver oils, and, to a lesser extent, egg yolks and animal fats. Populations with access to these foods could partially compensate for low sunlight. This reduced selective pressure on skin pigmentation. As a result, some high-latitude populations retained darker skin tones because their diets supplied sufficient vitamin D. This dietary buffering helps explain why skin colour does not correlate perfectly with latitude. Inland populations relying heavily on plant foods or animals low in vitamin D face stronger pressure to adapt through skin pigmentation. Coastal and riverine populations with fish-rich diets faced less pressure. Culture and subsistence strategies interacted with biology, shaping outcomes in different ways. Clothing further intensified vitamin D challenges. As humans adapted to colder climates, they covered more of their skin for warmth. This reduced UV exposure regardless of skin tone. In such conditions, pigmentation changes affecting exposed areas like the face and hands became particularly relevant. Even small increases in UV penetration in these regions could contribute to vitamin D synthesis during brief periods of sunlight. Seasonality amplified these effects. In northern latitudes, vitamin D production often occurred almost exclusively during summer. The body needed to produce and store enough vitamin D during this time to last through the winter. Individuals whose skin allowed faster synthesis during these months had an advantage. This advantage might only manifest months later, during pregnancy or early childhood, when stored vitamin D was critical. The pressure exerted by vitamin D scarcity did not act alone. It interacted with other stresses, including cold, nutritional limitations, and disease. But because vitamin D influences so many systems, its effects rippled outward, touching multiple aspects of health at once. This made it a powerful, if invisible, selective force. From a genetic perspective, multiple genes influence how the skin produces and distributes melanin. Variants affecting these genes arose randomly through mutation. In tropical environments, many of these variants had little impact on survival. In northern environments, some became advantageous. Over time, natural selection favoured combinations of variants that reduced melanin production, enough to improve vitamin D synthesis, without completely eliminating UV protection. Importantly, different populations achieved similar outcomes through different genetic routes. The genes involved in lighter skin pigmentation in European populations differ in some respects from those involved in East Asian populations. This demonstrates that lighter skin was not inherited from a single ancestral source, but evolved independently in response to similar pressures. This independent emergence reinforces a key point. Skin colour is not a marker of shared destiny or hierarchy. It is a response to local conditions. Where light was scarce and diets could not fully compensate, skin lightened. Where light remained strong or diets supplied vitamin D, darker pigmentation persisted. The relationship between vitamin D and bones offers a clear illustration of how invisible pressures shape visible traits. Bones record the consequences of long-term deficiency, but they do not announce it in advance. Skin, by adjusting pigmentation, acted as an upstream modifier, altering the input that affected bone health downstream. For individuals living through these changes, none of this would have been apparent. People did not connect bone deformities to sunlight or skin tone. They responded to immediate realities, caring for the sick, adapting their practices, and passing on knowledge within their communities. Evolution operated alongside culture, not in opposition to it. From a modern perspective, it can be tempting to see vitamin D deficiency as a simple problem with a simple solution. Today, supplements and fortified foods can correct it easily. But in deep time, no such options existed. The body had to solve the problem using the tools it had. Skin pigmentation was one of those tools. As humans continued to live in northern latitudes, the balance between protection and absorption continued to adjust. In some regions, extreme light scarcity pushed pigmentation toward very light tones. In others, moderate scarcity led to intermediate tones. These outcomes were not goals. They were side effects of adaptation. The idea of invisible pressure helps explain why these changes happened without intention or awareness. Vitamin D did not announce itself. It did not punish immediately. It nudged populations slowly, shaping outcomes across generations rather than lifetimes. This is how many of the most important evolutionary changes occur, quietly, persistently, without drama. Evolution rarely solves problems cleanly. It does not arrive with a single answer that works everywhere, forever. Instead, it negotiates. It balances competing demands, accepts imperfect solutions, and adjusts slowly as conditions change. When it comes to human skin colour, this negotiation took the form of a long compromise between two opposing needs. On one side was protection from the sun's damaging effects. On the other was absorption of sunlight to support vital biological processes. Neither need could be ignored, and neither could be fully satisfied at the same time. What emerged was not an ideal state, but a workable one, shaped by geography, time, and chance. To understand this compromise, it helps to revisit what the skin was being asked to do. In environments with intense sunlight, especially near the equator, ultraviolet radiation posed a constant threat. It damaged DNA, increased mutation rates in skin cells, and degraded folate, a nutrient essential for healthy reproduction. High levels of melanin offered protection against these dangers. They reduced UV penetration, preserved folate, and helped maintain cellular integrity. In these conditions, protection was the dominant concern and darker skin was favoured. As humans moved into regions with less sunlight, the balance shifted. Ultraviolet radiation became weaker and more seasonal. Vitamin D synthesis, which depends on UVB exposure, became less reliable. In these environments, absorbing enough sunlight became just as important as protecting against it. Skin that blocked too much UVB could leave the body short of vitamin D, leading to weakened bones, compromised immune function, and reproductive challenges. Here, absorption gained importance. The problem was that these two needs pulled in opposite directions. Increasing melanin improved protection but reduced absorption. Decreasing melanin improved absorption but reduced protection. There was no setting that maximised both. Evolution's task was not to eliminate one need in favour of the other, but to find a balance that worked well enough under local conditions. This balance point varied by environment. Near the equator, the optimal compromise favoured high melanin. In far northern regions, it favoured lower melanin. In between, a wide range of intermediate states existed. This is why human skin colour does not fall into discrete categories. It exists along a gradient, reflecting many local compromises rather than a single global solution. The speed at which these compromises emerged was slow by any human standard. Changes in skin pigmentation unfolded over thousands of years. Each generation differed only slightly from the one before it. No individual experienced a dramatic shift. Instead, small genetic variations accumulated, guided by differences in survival and reproduction that were often subtle. At the genetic level, skin pigmentation is influenced by many genes, each contributing a small effect. Some affect how much melanin is produced. Others affect how melanin is packaged within cells or how it responds to sunlight. Mutations in these genes arise randomly. Most have little or no effect. A few slightly alter pigmentation. In a given environment, some of these alterations turn out to be useful. In low UV environments, variants that reduced melanin production by a small amount could improve vitamin D synthesis without eliminating UV protection entirely. These variants did not make skin suddenly light. They nudged it in that direction. Over time, as such variants became more common, the average pigmentation of the population shifted. Crucially, this process did not require lighter skin to be universally beneficial. It only required it to be beneficial on average under specific conditions. Individuals with slightly lighter skin did not necessarily live longer or healthier lives in every case. They simply had marginally better outcomes often enough for the trait to spread. This is how compromise works in evolution. It does not select the best possible trait. It selects traits that are good enough often enough. Trade-offs are accepted because there is no alternative. One of the reasons this compromise was so slow is that the pressures involved were rarely acute. Vitamin D deficiency does not usually cause immediate death. UV damage does not always result in catastrophic failure. Both exert their influence gradually, over years and across generations. This makes the selective pressure persistent but gentle, allowing multiple solutions to coexist for long periods. Culture added another layer of complexity. Clothing, shelter, diet, and behaviour all influenced how much sunlight people received and how dependent they were on skin-based vitamin D synthesis. These cultural practices could buffer or amplify biological pressures. For example, diets rich in vitamin D reduced the need for lighter skin in low UV environments. Heavy clothing increased the need for efficient absorption in exposed areas. Seasonal migration altered exposure patterns. Because culture changes faster than biology, it sometimes outpaced genetic adaptation. This created mismatches, where bodies shaped by one environment found themselves living under different conditions. Evolution responded, but always with a delay. The compromise was continually adjusted, but never perfected. Another important aspect of this negotiation is that it was not symmetrical. The cost of too little protection in high UV environments was often greater than the cost of too little absorption in moderate environments. Severe folate deficiency can have immediate reproductive consequences. Severe UV damage can compromise health early in life. As a result, high melanin levels remain strongly favoured near the equator, while lower melanin levels emerge more gradually elsewhere. This asymmetry helps explain why very dark skin persisted in equatorial regions, despite migrations and genetic mixing. The protective benefits remained crucial. In contrast, lighter skin emerged primarily in regions where UV scarcity made absorption the limiting factor. It also helps explain why skin colour changes often lagged behind migration. Early humans entering new environments carried pigmentation adapted to their previous conditions. It took many generations for the balance of pressures to shift enough to favour new compromises. During this time, populations lived with suboptimal solutions, relying on culture and behaviour to compensate. The compromise between protection and absorption also operated within individuals, not just across populations. Skin can respond to sunlight by increasing melanin production, a process we recognise as tanning. This response provides short-term protection against UV damage, but reduces vitamin D synthesis. The body adjusts dynamically, but always within limits. Tanning does not fully replicate the effects of genetically determined pigmentation, but it reflects the same underlying trade-off. This dynamic response highlights an important point. Skin pigmentation is not fixed in a rigid sense. It is regulated, responsive, and context-dependent. Genetics sets a range. Environment determines where within that range an individual falls at a given time. Evolution shapes the range itself over long periods. The idea of compromise also challenges simplistic narratives about adaptation. It is tempting to frame lighter skin as a straightforward improvement in low UV environments. In reality, it introduced new vulnerabilities. Reduced melanin increased susceptibility to UV damage during periods of high exposure, such as summer or sudden migration back to sunnier regions. It increased the risk of skin cancers later in life. These risks were tolerated because the benefits to reproduction and early life health outweighed them. This tolerance of late life costs is common in evolution. Traits that improve reproductive success can persist even if they increase problems after reproduction. The compromise favoured early life benefits over long-term protection, a pattern seen in many aspects of human biology. Importantly, the compromise was never finalised. Even today, human skin pigmentation reflects ongoing negotiation. Modern lifestyles with indoor living, artificial lighting, global travel and varied diets have altered the balance of pressures. In many cases, biology has not caught up. Vitamin D deficiency can occur in both dark and light-skinned populations living outside their ancestral environments. UV damage can affect light-skinned individuals living in high UV regions. These modern mismatches remind us that skin colour is not an indicator of suitability or resilience in any absolute sense. It is a historical record of compromises made under specific conditions that may no longer apply. Throughout this long process, there was no single moment when evolution chose absorption over protection or vice versa. The choice was always contextual. In some regions, protection remained dominant. In others, absorption gained ground. In many places, the balance hovered in between. This perspective helps dissolve the idea that skin colour differences represent deep biological divisions. They do not. They represent different solutions to the same basic problem: how to interact with sunlight in a way that supports survival and reproduction. The underlying biology is shared. The variations are adjustments, not separations. As humans continued to spread, mix, and adapt, this compromise played out repeatedly. In some populations, lighter skin emerged quickly. In others, it did not. In still others, it reversed or blended through migration and intermarriage. The outcome was diversity, not uniformity. The slow pace of this process also meant that chance played a role. Which genetic variants happened to be present in a population influenced how it responded to environmental pressure. Two populations in similar environments could arrive at similar pigmentation through different genetic pathways. This reinforces the idea that evolution works with what is available rather than aiming toward a predetermined goal. The negotiation between protection and absorption did not end when humans settled into northern latitudes. It continued as environments changed, cultures evolved, and populations interacted. Skin colour remained a variable trait, always adjusting, never reaching a final form, and in that ongoing adjustment, the story of human diversity continued to unfold, guided not by ideals or intentions, but by the quiet mathematics of survival under changing light. When people first encounter the idea that lighter skin did not arise a single time, in a single place, from a single ancestral group, it often feels counterintuitive. There is a strong tendency to imagine human traits as branching neatly, with one origin point and a clear line of descent. But human evolution rarely follows such tidy paths. Instead, It resembles a series of overlapping experiments shaped by local conditions and constrained by what genetic material happened to be available at the time. Lighter skin is one of the clearest examples of this pattern. It did not appear once and spread everywhere. It appeared multiple times independently as different populations faced similar environmental pressures and arrived at similar compromises through different routes. To understand why this happened, it helps to step away from the idea of skin colour as a single trait. What we casually refer to as light skin is not produced by one gene or one biological switch. It is the result of many small changes affecting melanin production, distribution, and regulation. These changes can occur in different combinations, leading to broadly similar outcomes without identical genetic histories. In other words, skin can become lighter in more than one way. As humans dispersed into regions with lower ultraviolet radiation, particularly in Europe and East Asia, the same fundamental challenge emerged. The sun was weaker for much of the year, vitamin D synthesis was less reliable, and the balance between protection and absorption shifted. In these environments, populations with slightly reduced melanin levels had an advantage. That advantage did not depend on how the reduction was achieved, only that it occurred. In Europe, genetic studies have identified several genes that played a significant role in lightening skin pigmentation over time. Some of these genes affect how much melanin is produced. Others influence how melanin is transported within skin cells. Variants of these genes became more common because they allowed more efficient vitamin D synthesis under low UV conditions. Importantly, these variants were not present at high frequency when humans first arrived in Europe. They increased gradually over thousands of years. In East Asia, a different set of genetic changes contributed to lighter skin. While the end result, reduced pigmentation, appears similar, the underlying genetic pathways are not identical to those seen in European populations. This means that light skin in East Asia and light skin in Europe are not inherited from a single shared light-skinned ancestor. They are parallel outcomes shaped by similar pressures acting on different genetic backgrounds. This phenomenon is known in evolutionary biology as convergent evolution. It occurs when different populations or species develop similar traits independently because they face similar challenges. Wings evolved independently in birds, bats, and insects. Camera-like eyes evolved independently in vertebrates and cephalopods. In the same way, lighter skin evolved independently in different human populations as a response to low UV environments. What makes this particularly important is that it undermines any attempt to treat skin colour as a marker of deep biological division. If the same visible trait can arise through different genetic routes, then appearance alone tells us very little about shared ancestry. Two people with similarly light skin may be genetically less similar to each other than either is to someone with darker skin from a different region. Skin colour, in this sense, is a poor proxy for overall genetic similarity. The timing of these changes also matters. Lighter skin did not appear immediately after humans entered new regions. In Europe, for example, early hunter-gatherers retained relatively dark skin for thousands of years after arriving at higher latitudes. Genetic evidence suggests that some of the most significant pigmentation changes occurred relatively recently, within the last 10,000 years, coinciding with shifts in diet and lifestyle. The adoption of agriculture altered human nutrition in profound ways. As populations began relying more heavily on cultivated plants and less on wild game and fish, their intake of vitamin D decreased. Plant-based diets are generally low in vitamin D. This dietary shift intensified selective pressure on skin pigmentation, making efficient vitamin D synthesis through sunlight even more important. In this context, lighter skin became more advantageous than it had been for earlier foragers with more varied diets. This helps explain why lighter skin became widespread in some regions only after agriculture took hold. The pressure was not simply latitude, but the interaction of latitude with diet. In regions where people continued to consume vitamin D-rich foods, such as fish or marine mammals, Darker skin could persist even at high latitudes. In regions where diets shifted toward grains and legumes, skin pigmentation adapted more strongly to compensate for nutritional loss. East Asia presents a similar but distinct pattern. Populations there experience different agricultural histories, different staple crops, and different subsistence strategies. These differences influenced how strongly vitamin D scarcity shaped biology. As a result, pigmentation changes followed different timelines and pathways, even under similar sunlight conditions. Another factor contributing to multiple origins of lighter skin is genetic variation itself. Different populations carry different sets of mutations simply due to chance. When selective pressure favoured reduced melanin, evolution worked with whatever variants were already present. If one population had mutations affecting a particular gene, those mutations could be amplified. Another population might rely on a different gene entirely. The outcome, lighter skin, could look similar even though the underlying biology differed. This role of chance is often underestimated. Evolution is not a guided process. It does not search for the best possible solution. It selects from available options. Two populations facing the same problem may solve it differently, because they start with different genetic toolkits. This is why human variation is so complex and resistant to simple classification. It is also important to note that lighter skin did not always emerge to the same degree. The spectrum of pigmentation in Europe differs from that in East Asia, and both differ from patterns seen in Central Asia or the Americas. These differences reflect varying balances between sunlight, diet, cultural practices, and genetic history. There is no single endpoint that evolution was aiming toward. The Americas offer another perspective. Indigenous populations of the Americas descended from groups that migrated from northeastern Asia across Beringia. These populations experienced a range of UV environments as they spread southward. Skin pigmentation in the Americas reflects this diversity, with darker tones near the equator and lighter tones at higher latitudes, though the pattern is influenced by relatively recent migration history and dietary factors. Again, pigmentation adjusted locally rather than following a single inherited template. What emerges from all of this is a picture of repeated adaptation rather than linear progression. Lighter skin is not a marker of advancement, nor is it a sign of a shared destiny. It is one of many ways the human body has responded to environmental constraints. The fact that it emerged more than once reinforces how strongly those constraints shaped biology. This perspective also helps explain why skin colour variation remains so fluid. Human populations have always moved, mixed, and adapted. Traits that were advantageous in one context can become less so in another. Migration reintroduces genetic diversity. Cultural changes alter selective pressures. The compromise between protection and absorption is constantly renegotiated. In modern times, this negotiation has become even more complex. Artificial lighting, indoor lifestyles, sunscreen use, clothing, global travel, and dietary supplementation have radically altered the relationship between humans and sunlight. Many people now live in environments very different from those their ancestors adapted to. As a result, vitamin D deficiency can affect people across the pigmentation spectrum, while UV-related skin damage can occur in populations with little ancestral exposure to intense sunlight. These modern mismatches highlight an important point. Skin colour is not destiny. It does not determine health, capability, or worth. It reflects historical conditions that may no longer apply. Understanding how and why lighter skin emerged more than once helps dismantle myths that have attached social meaning to biological variation. It also reminds us that evolution is opportunistic rather than purposeful. The same challenge, encountered in different places, can yield similar outcomes through different paths. Human diversity is the result of many such paths intersecting, overlapping, and diverging over time. The emergence of lighter skin more than once is not a mystery when viewed through this lens. It is a natural consequence of humans being a flexible, mobile species, carrying a shared biology into varied environments and adjusting it as needed. The repetition of this outcome does not point to inevitability or hierarchy, it points to adaptability. And as we move forward, that adaptability continues to reveal itself, not as a finished product, but as an ongoing process, shaped by environments that change faster than biology can follow, leaving the story of human skin always unfinished, always in motion, always responding to light that is never quite the same from one place to the next. As humans pushed farther into higher latitudes, the challenge they faced was no longer simply weaker sunlight. It was unpredictability layered on top of scarcity. Ice reshaped landscapes. Clouds thickened skies for weeks at a time. Winters stretched longer, darker, and colder than anything earlier humans had experienced. Sunlight did not just grow faint, it became intermittent, filtered, and unreliable, arriving in brief windows that could not be taken for granted. In these conditions, the relationship between the human body and light changed again, not abruptly, but persistently, pressing on biology in ways that were subtle yet relentless. Ice played a central role in this shift. During repeated glacial periods, vast ice sheets expanded across northern continents. Even in regions not covered directly by ice, the climate was colder and drier. Snow blanketed the ground for long periods, reflecting visible light but doing little to increase biologically useful ultraviolet radiation. Ice altered wind patterns, ocean currents, and cloud formation, reshaping regional climates far beyond the edges of glaciers themselves. For people living in these environments, sunlight was not only weaker because of latitude, it was further diminished by atmospheric conditions that blocked or scattered UV radiation before it reached the ground. Cloud cover matters more than most people realise. Thick, persistent clouds can reduce UVB exposure dramatically, even during daylight hours. In northern regions influenced by glacial climates, cloudiness was often the norm rather than the exception. Days might be technically bright but biologically dim, offering little opportunity for vitamin D synthesis. When these conditions persisted year after year, generation after generation, the pressure they exerted accumulated quietly. Winter magnified all of this. At high latitudes, winter does not simply bring colder temperatures, it fundamentally alters the light environment. Day length shrinks. The sun's arc across the sky lowers further. In some regions, the sun barely rises at all for weeks. During these periods, UVB radiation drops to nearly zero. No amount of time spent outdoors can compensate. Vitamin D production in the skin effectively stops. This seasonal shutdown forced the human body into a new pattern. Vitamin D had to be produced and stored during the brighter months, then rationed through the winter. Any factor that improved production during summer became more important. Skin pigmentation played a role here, because lighter skin could synthesize vitamin D more rapidly when UVB was available. In environments with short summers, speed mattered. Ice Age environments also imposed energetic costs. Cold temperatures increased metabolic demands. Maintaining body heat required calories. Hunting and gathering became more challenging. Food scarcity during winter was common. Under these conditions, the body had fewer resources to compensate for nutritional deficiencies. Vitamin D deficiency layered itself onto other stresses, compounding their effects. Children growing up in these environments were especially vulnerable. Bone development depends heavily on adequate vitamin D and calcium. In long, dark winters, children with insufficient vitamin D stores could develop weakened skeletons. This did not always result in dramatic deformities, but even subtle weakening could increase injury risk or reduce physical resilience. Over time, these small disadvantages could influence survival rates. Pregnancy added another layer of sensitivity. Vitamin D plays a role in fetal skeletal development and maternal health. In populations where winter pregnancies coincided with depleted vitamin D stores, complications could arise. Pelvic shape, influenced by bone development earlier in life, affected childbirth outcomes. These reproductive consequences, though rarely traced to a single cause, influenced which traits were passed on. Ice and cold also shaped behaviour. People spent more time indoors or sheltered. Fire became essential not just for cooking but for warmth and light. Shelters reduced exposure to the elements, but they also reduced exposure to sunlight. Clothing covered most of the body year-round. Skin that might have been exposed during daily activity in warmer climates was now hidden beneath layers. This made efficient vitamin D synthesis through limited exposed areas even more important. Clouds and snow further complicated the picture. While snow reflects visible light and can make landscapes appear bright, it does not significantly increase UVB exposure. In fact, cold conditions often encourage people to cover exposed skin, negating any potential benefit. The brightness of snowy environments can be misleading, offering the illusion of abundant light without the biological effects that matter for vitamin D production. In these conditions, the pressure toward lighter skin intensified in some populations. Reduced melanin allowed more UVB penetration during brief periods of exposure. This did not eliminate winter deficiency, but it improved summer production and storage. Over many generations, this advantage became meaningful. It is important to emphasize that this was not a universal outcome. Ice Age conditions varied regionally. Some areas experienced heavy glaciation and persistent cloud cover. Others remained relatively milder, even at similar latitudes. Local geography, proximity to oceans, and prevailing winds all influenced climate. As a result, selective pressures on skin pigmentation differed from place to place. Diet continued to play a moderating role. Populations with access to vitamin D-rich foods, particularly marine resources, were less dependent on sunlight. In Arctic and subarctic regions, diets high in fish, seal and whale fat provided substantial vitamin D. These populations often retained darker skin despite extreme light scarcity. Their biology adapted through dietary pathways rather than pigmentation changes. In contrast, inland populations relying on terrestrial animals and plant foods faced greater challenges. Their diets provided less vitamin D, increasing reliance on sunlight. In these contexts, skin pigmentation became a more significant variable in maintaining vitamin D balance. Ice Age environments also influenced migration patterns. During glacial maxima, ice sheets blocked certain routes while exposing others through lower sea levels. Human groups moved, paused, and regrouped in response. These movements mixed populations with different pigmentation traits, introducing new genetic variation. In some cases, lighter skin traits spread through gene flow rather than local adaptation. In others, they emerged independently under similar pressures. The interplay between ice, clouds, and long winters illustrates how environmental factors rarely act in isolation. Latitude set the baseline for UV availability. Climate modified it. Culture responded to both, altering behavior and diet. Biology responded to the combined effect. Skin pigmentation sat at the intersection of these forces, adjusting slowly as conditions demanded. This complexity helps explain why skin colour patterns today are intricate rather than uniform. Even within Europe, pigmentation varies along north-south and east-west gradients, reflecting differences in cloud cover, climate history, diet, and migration. Northern coastal regions differ from inland areas. Mountainous regions differ from lowlands. These patterns are legacies of past environments as much as present ones. Long winters also shaped how humans experienced time and seasonality. Life became structured around cycles of scarcity and abundance. Summer activity intensified. Winter demanded conservation. These rhythms influenced reproduction, child-rearing, and social organization. Vitamin D scarcity became part of this seasonal rhythm, rising and falling with the sun. From the perspective of evolution, the key factor was consistency. A single harsh winter mattered little. Repeated winters across many generations created stable pressure. Traits that improved outcomes under these conditions accumulated slowly. Skin lightening was one such trait, but it was never the only one, nor was it always the most important. It is also worth noting that Ice Age conditions were not permanent. Glacial periods waxed and waned. Ice retreated and advanced. Sunlight patterns shifted accordingly. Populations adapted to one set of conditions sometimes found themselves in another. This dynamic environment favoured flexibility rather than extreme specialisation. This flexibility is evident in the fact that human skin retains the capacity to tan, even in populations with genetically lighter pigmentation. The underlying melanin system remains intact. Evolution adjusted baseline levels, not the entire mechanism. This allowed individuals to respond to short-term increases in UV exposure, even as long-term adaptations addressed chronic scarcity. As ice reshaped continents and clouds muted the sky, the sun became a limited resource, rationed by season and weather. The human body responded not with a single dramatic change, but with a series of small adjustments, each contributing to a slightly better fit between biology and environment. Skin pigmentation shifted as part of this process, influenced by the need to capture enough light when it was available. These adaptations did not resolve all challenges. Vitamin D deficiency likely remained common during long winters, but evolution does not eliminate problems. It reduces them enough to allow populations to persist. In that sense, lighter skin in some northern populations represents not a solution, but a mitigation, one that worked well enough under difficult conditions. As humans settled into colder, darker environments, sunlight was no longer the only force shaping their biology. Another set of changes was unfolding alongside shifts in climate and latitude. Changes driven not by the sky, but by human behaviour. Diet transformed. Fire became central to daily life. Food was cooked, stored, shared, and planned for in new ways. These cultural innovations did not replace biology, but they altered the pressures acting upon it, subtly changing how the body related to sunlight and how strongly skin pigmentation was shaped by it. For early humans living in tropical and subtropical environments, diet was diverse and opportunistic. Fruits, tubers, leaves, insects, and hunted animals all contributed nutrients. Sunlight reliably supplied vitamin D, so diet did not need to. This balance shifted as humans moved northward and encountered seasonal scarcity. Winters reduced plant availability. Cold limited foraging. Survival increasingly depended on animal foods, stored resources, and technological strategies rather than constant environmental abundance. Fire played a central role in this transition. Long before humans reached northern latitudes, fire was already being used, but in colder environments it became essential rather than optional. Fire provided warmth, protection, light, and a way to transform food. Cooking altered the nutritional profile of what humans ate. It increased caloric availability, improved digestibility, and reduced pathogens. Over time, cooked diets supported changes in jaw structure, teeth, and gut length. But cooking also affected vitamin intake, sometimes enhancing it, sometimes reducing it. When food is cooked, certain vitamins degrade. Vitamin C, for example, is sensitive to heat. Vitamin D, however, is relatively stable. The bigger issue was not loss during cooking, but availability in the first place. Most plant foods contain little or no vitamin D. Terrestrial animal meat contains small amounts, but not enough to meet needs under low sun conditions. Fatty fish and marine mammals are rich sources, but these were not universally available. As diets shifted toward cultivated plants during the later adoption of agriculture, vitamin D intake often decreased further. Grains and legumes became staples, providing calories but few micronutrients. In regions where dairy consumption emerged, some compensation occurred, but this was uneven and came much later. For much of human history, sunlight remained the primary source of vitamin D, even as diets changed. Fire also altered daily routines. In colder climates, people spent more time near hearths and inside shelters. Evening activities extended beyond daylight hours. Artificial light from fire allowed social interaction, tool making and storytelling after sunset, but it did not provide UV radiation. Time spent indoors increased. Skin exposure to sunlight decreased. This cultural shift intensified the body's dependence on efficient vitamin D synthesis during limited daylight hours. Clothing added another layer. Fire made it possible to process animal hides and later textiles more effectively, producing garments that insulated the body from cold. These coverings were life-saving, but they further reduced skin exposure. In tropical regions, minimal clothing allowed sunlight to reach much of the body. In northern regions, only the face and hands might be exposed for much of the year. This made pigmentation changes affecting these areas particularly relevant. The combined effect of diet, fire, and clothing reshaped the relationship between humans and sunlight. Sun exposure became less frequent, more seasonal, and more constrained by behavior. Under these conditions, skin pigmentation adjustments that improved UV absorption in exposed areas gained importance. However, these cultural adaptations also introduced variability. Different groups adopted different diets. Some relied heavily on hunting large land animals, others focused on fishing or coastal foraging. Some stored food extensively, others moved seasonally. Each strategy influenced vitamin D availability differently. Populations with diets rich in marine resources experienced a different balance. Fish liver oils, fatty fish, and marine mammals provided substantial vitamin D. In these groups, reduced sunlight exposure mattered less. Skin pigmentation remained darker even at high latitudes because the dietary pathway compensated for UV scarcity. This is a critical reminder that biology does not respond to sunlight alone. It responds to the total nutritional and environmental context. Fire also influenced migration patterns. The ability to cook and stay warm expanded the range of environments humans could inhabit. People moved into regions that would have been inaccessible without fire. This accelerated exposure to low UV conditions, increasing selective pressure on pigmentation in some populations while allowing others to buffer that pressure through diet. Agriculture intensified these dynamics. When humans began cultivating crops, they altered landscapes and food systems. Settled life reduced mobility. Time spent outdoors changed. Diets became more monotonous. In many regions, reliance on grains reduced intake of vitamin D-rich foods. This made sunlight-based synthesis more critical, particularly for children and pregnant individuals. Archaeological and genetic evidence suggests that some of the most pronounced skin lightening occurred after the adoption of agriculture in certain regions. This timing aligns with increased vitamin D stress rather than with latitude alone. It suggests that cultural change can amplify biological pressure, accelerating adaptation. Fire and cooking also influenced social organisation. Shared meals reinforced group cohesion. Food preparation became structured. Seasonal planning became essential. These social changes affected reproduction, childcare and survival, indirectly shaping evolutionary outcomes. Traits that supported health under these new conditions gained importance. The changing relationship with sunlight was not simply a loss, it was a trade. Fire and shelter reduced exposure to cold and predators. Clothing prevented hypothermia. Cooking improved energy intake. These benefits outweighed the costs, even if they introduced new challenges. Evolution does not judge trade-offs morally. It follows outcomes. Skin pigmentation adjustments should be seen within this broader context. Lighter skin did not emerge solely because the sun was weaker. It emerged because human behaviour made the sun less accessible. Culture reshaped the environment to which biology had to adapt. This interplay between culture and biology is sometimes misunderstood as one replacing the other. In reality, they operate together. Culture can create new selective pressures just as climate can. Fire did not free humans from evolution. It redirected it. The pace of these changes remained slow. Even as diets and technology shifted rapidly by evolutionary standards, genetic adaptation lagged behind. Populations lived for many generations with mismatches between biology and lifestyle. Skin pigmentation adjustments reduced some of that mismatch, but never eliminated it entirely. This helps explain why vitamin D deficiency persists today, even in populations whose ancestors adapted to low UV environments. Modern lifestyles have further reduced sun exposure. Indoor living, sunscreen use, and urban design limit UV access. Diets vary widely. Biology continues to operate under assumptions shaped by past environments, not present ones. The story of diet and fire underscores a key point. Skin colour is not just about where humans lived, it is about how they lived. The tools they used, the foods they ate, the shelters they built, and the rhythms of their daily lives all influenced how much sunlight reached their skin and how important pigmentation adjustments became. As humans continued to modify their environments, the selective landscape grew more complex. Some pressures intensified, others softened. Skin pigmentation responded where it mattered most, but it was only one variable among many. When people talk about evolution, it is easy to imagine sweeping transformations, dramatic changes unfolding like scenes in a documentary montage. But at the level where evolution actually operates, nothing moves quickly or cleanly. There are no grand redesigns. There are only tiny changes scattered across generations, most of them barely noticeable, many of them doing nothing at all. Human skin colour changed not because evolution decided it should, but because thousands of very small genetic shifts accumulated over immense spans of time, each one nudging biology slightly in one direction or another. Genes are the instruction cells used to build and regulate the body. They do not work in isolation. Most traits, especially complex ones like skin pigmentation, are influenced by networks of genes interacting with each other and with the environment. There is no single skin colour gene. Instead, there are many genes that influence how much melanin is produced, how it is distributed, how melanocytes respond to sunlight, and how pigment is packaged inside skin cells. Each gene contributes a small part of the overall outcome. Mutations are the raw material of this process. A mutation is simply a change in DNA sequence. Most mutations are neutral. They do not improve or worsen survival. Some are harmful. A very small number turn out to be beneficial under specific conditions. Mutations arise randomly without regard for need. Evolution does not create mutations in response to challenges. It filters the ones that happen to appear. In the context of skin pigmentation, mutations that slightly reduced melanin production were neither good nor bad in tropical environments. They offered no advantage and sometimes posed risks, so they tended not to spread widely. But as humans moved into environments with lower ultraviolet radiation, those same mutations could become useful. A slight reduction in melanin allowed more UVB to penetrate the skin, supporting vitamin D synthesis. Under these conditions, the mutation's effect shifted from neutral to beneficial. This shift in usefulness is critical to understanding why pigmentation changed so slowly. Mutations did not suddenly appear when humans entered new environments. Many were already present at low frequencies. What changed was the environment's response to them. The same genetic variant that once did nothing now made a small difference. Over generations, that difference mattered. Each generation introduced new mutations and reshuffled existing ones through reproduction. Most individuals carried a mix of variants, some inherited from one parent, some from the other. No single person embodied a complete solution. Instead, populations drifted gradually as certain variants became more common. Genetic drift also played a role. In small populations, chance can influence which traits spread. A mutation might become common simply because its carriers happen to have more offspring, even if the mutation itself had little effect. When combined with selective pressure from the environment, drift could accelerate or slow changes unpredictably. This is one reason why pigmentation patterns vary even among populations living in similar environments. The cumulative effect of these tiny shifts is difficult to grasp because it does not follow a straight line. Skin did not steadily lighten in a smooth progression. There were pauses, reversals, and plateaus. Migration mixed populations with different pigmentation levels. Changing diets altered selective pressures. Climate fluctuations reshaped UV availability. Through all of this, genes continue to shuffle and mutate, producing variation that selection could act upon. One important aspect of this process is that changes rarely affected all parts of the body equally. Some genetic variants influence pigmentation more strongly in certain regions, such as the face, arms, or hands. These areas were more likely to be exposed to sunlight in clothed populations, making them especially relevant for vitamin D synthesis. Over time, visible differences emerged unevenly, reflecting patterns of exposure rather than a uniform body-wide change. Another key point is that pigmentation genes often have multiple effects. A mutation that alters melanin production might also influence immune function, inflammation, or cellular stress responses. These side effects could amplify or counteract the mutation's primary effect. Evolution does not isolate traits, it evaluates the whole package. Because of this, some mutations that lighten skin may have spread not only because of their effect on vitamin D, but because they interacted favourably with other systems. Others may have been constrained because they carried hidden costs. This complexity further slowed the process and produced diverse outcomes. Over thousands of years, the accumulation of many small effect mutations led to noticeable differences between populations. But even then, those differences were relative, not absolute. The genetic distance between people with different skin tones is small compared to the genetic variation shared across all humans. Most genetic differences occur within populations rather than between them. Skin colour represents a tiny fraction of overall human genetic diversity. It is also important to understand that these genetic changes did not erase the ancestral pigmentation system. The machinery for producing melanin remained intact. What changed were regulatory settings, thresholds, and sensitivities. This is why people with lighter ancestral pigmentation can still tan, and people with darker ancestral pigmentation can experience vitamin D deficiency in low UV environments. The system was adjusted, not replaced. The slow pace of genetic change also explains why skin colour adaptations often lagged behind environmental change. Humans could move into new regions within a few thousand years. Genetic adaptation might take much longer. During that gap, populations relied on cultural solutions such as diet and clothing to survive. Genetic changes followed later, smoothing some of the rough edges but never fully catching up. This lag is a recurring theme in human evolution. Culture moves faster than biology. Fire, tools, agriculture, and technology altered environments rapidly. Genes responded slowly. Skin pigmentation sits at the intersection of this mismatch. It reflects environments that shaped ancestors over long periods, not necessarily the conditions people live in today. Another reason these changes took so long is that selection pressure was rarely extreme. Vitamin D deficiency increased risk, but it did not wipe out populations. UV damage posed dangers, but it was not universally lethal. These pressures were enough to guide evolution, but not enough to force rapid change. This allowed multiple pigmentation levels to coexist for long periods. The idea of tiny shifts is not just metaphorical. Many pigmentation-related genetic variants alter melanin production by a few percent. On their own, these changes are barely noticeable. Combined across many genes and many generations, they produce visible differences. Evolution builds complexity from accumulation, not leaps. This accumulation also means that no clear boundary exists between pigmentation categories. There is no genetic point at which skin becomes light or dark. There are only ranges shaped by overlapping variants. This is why attempts to classify humans into discrete biological races based on skin colour fail scientifically. The underlying genetics do not support such divisions. From the perspective of deep time, the emergence of lighter skin is not a story of transformation but of tuning. The human body adjusted dials that were already present. It did so gradually, unevenly and repeatedly, depending on where populations lived and how they lived. As these genetic shifts continued, they interacted with other evolutionary changes. Body proportions adapted to climate, metabolism adjusted to diet, immune systems responded to local pathogens. Skin pigmentation evolved as part of this broader mosaic, not as a standalone trait. Looking forward, the story does not end with these changes. Human populations continue to migrate, mix, and adapt. New mutations continue to arise. Old ones persisted or faded. Skin color remained flexible, responsive, and variable. Understanding genes and mutations in this way strips away the illusion of intention. There was no plan, no direction, no ideal outcome. There was only variation filtered through survival and reproduction under specific conditions. Lighter skin emerged because many small genetic shifts happened to align with environmental pressures in certain places, often more than once, over long spans of time. If you were to travel slowly across the surface of the Earth, moving on foot rather than by airplane, one quiet truth would reveal itself long before any map lines or national borders did. Skin colour does not change abruptly. It does not jump from one shade to another at invisible boundaries. Instead, it shifts gradually, almost imperceptibly, deepening or lightening over distance and time. This gradual change is not an accident, nor is it a flaw in how humans are classified. It is the natural outcome of how evolution works when it responds to continuous environmental variation rather than discrete categories. The idea that skin colour exists along a gradient rather than a simple line is one of the most important concepts for understanding human variation. Yet it is often obscured by the way humans like to sort, label and simplify. Language encourages binaries. Culture encourages boxes. Biology does neither. Biology responds to pressures that themselves vary continuously, and sunlight is one of the most continuous variables on the planet. Ultraviolet radiation does not switch on or off at a particular latitude. It declines gradually as you move away from the equator. The angle of the sun changes by degrees, not steps. Cloud cover varies regionally. Altitude modifies exposure. Seasonal patterns overlap and blur. Even within the same latitude, two regions can receive very different amounts of biologically useful sunlight due to climate and geography. Evolution responds to this smooth landscape with smooth adjustments, not sharp breaks. Skin pigmentation reflects this reality. Populations whose ancestors lived under intense, consistent sunlight evolved higher baseline melanin levels. Populations whose ancestors lived under weaker, more seasonal sunlight evolved lower baseline levels. Between these extremes lies a wide spectrum of intermediate pigmentation, each point representing a local compromise between protection and absorption. There is no biological reason for skin colour to form discrete groups because the pressures shaping it never did. This gradient is reinforced by how genes work. As discussed earlier, skin colour is influenced by many genes, each contributing a small effect. These genes do not switch pigmentation from dark to light in a single step. They nudge it. Some increase melanin production slightly, others reduce it. Some affect distribution rather than quantity. The combined effect of dozens of such variants produces a continuous range of outcomes rather than a set of fixed categories. Because each gene operates on a spectrum, and because individuals inherit different combinations of variants, populations display overlapping ranges of skin tones. Two neighbouring populations may differ on average, but individuals from one may resemble individuals from the other. There is no clean dividing line. The gradient flows through them. Migration and mixing further smooth this gradient. Human populations have never been isolated for long on evolutionary timescales. People moved, traded, married, and had children across regions. These interactions blended genetic traits, including those affecting pigmentation. Even when populations adapted to local conditions, gene flow introduced variation from elsewhere, preventing sharp divergence. This constant mixing is one reason why skin colour gradients often follow geography rather than ancestry alone. A person's pigmentation reflects not just where their ancestors lived tens of thousands of years ago, but also more recent movements and interactions. The gradient is dynamic, reshaped continuously by human mobility. Another factor contributing to the gradient is the fact that different selective pressures dominate in different regions. In some places, UV intensity is the primary driver. In others, diet plays a larger role. In coastal regions with vitamin D-rich diets, darker pigmentation can persist at higher latitudes. In inland regions with plant-heavy diets, lighter pigmentation may be favoured at lower latitudes than expected. These local differences bend the gradient rather than breaking it. Altitude introduces further complexity. High-altitude regions receive stronger UV radiation due to thinner atmosphere, even at latitudes where UV would otherwise be moderate. Populations living at altitude often have darker skin than neighbouring lowland populations at the same latitude. This does not contradict the gradient model, it refines it. The gradient follows UV exposure, not latitude alone. Seasonality also matters. Regions with extreme seasonal variation experience periods of intense sunlight followed by long darkness. In these places, the balance between protection and absorption shifts across the year. Skin pigmentation in such populations reflects a compromise between summer UV damage and winter vitamin D scarcity. The result is often intermediate pigmentation rather than an extreme. The gradient model also explains why skin colour variation within populations can be substantial. Individuals differ in genetics, lifestyle and exposure. Some spend more time outdoors, some consume diets richer in vitamin D. Some inherit combinations of genes that push pigmentation slightly higher or lower than the population average. The gradient exists not just between populations but within them. This internal variation is often overlooked when people talk about skin colour in broad terms. Populations are described as if they were uniform, when in reality they're not. The gradient runs through families as well as across continents. Another reason skin colour does not form a simple line is that evolution does not aim for precision. It does not fine-tune traits to exact environmental measurements. It works with averages and probabilities. If a range of pigmentation levels all produce acceptable outcomes, they can coexist. There is no pressure to eliminate variation unless it becomes harmful. This tolerance for variation is especially important in traits like skin colour, where the costs and benefits are balanced rather than absolute. Being slightly too dark or slightly too light rarely results in immediate failure. It may increase risk under certain conditions, but those risks are often delayed or probabilistic. This allows a wide range of pigmentation levels to persist. The gradient is also shaped by the fact that skin colour adaptation often lags behind environmental change. When populations move into new regions, their pigmentation reflects their previous environment for many generations. During that time, cultural practices compensate. By the time genetic adaptation begins to catch up, environments may shift again. This constant lag prevents traits from settling into narrow optima. From a historical perspective, this gradient has been misinterpreted repeatedly. Humans have a tendency to impose categories onto continuous variation. These categories often reflect social boundaries rather than biological ones. Skin colour, being visible and variable, became an easy target for such classification. But the biology does not support the divisions imposed. Scientific attempts to classify humans into races based on skin colour failed because they ignored the gradient. They assumed sharp boundaries where none existed. Modern genetics has shown that these boundaries dissolve under scrutiny. Genetic variation changes gradually across geography, mirroring the patterns seen in pigmentation. Understanding skin colour as a gradient also helps explain why it is such a poor predictor of other traits. Because pigmentation is shaped primarily by sunlight and vitamin D balance, it tells us little about behaviour, intelligence, or capability. These traits are influenced by many other factors and do not follow the same gradients. The mistake of assuming otherwise has had profound social consequences. The gradient model also aligns with how the human body regulates pigmentation within individuals. Tanning is a response to increased UV exposure. It darkens the skin temporarily, shifting an individual along the gradient rather than flipping a switch. This flexibility reflects the underlying biology, which is designed to adjust rather than lock into fixed states. Even genetic differences associated with pigmentation often affect responsiveness rather than absolute colour. Some people tan easily, others burn, some darken gradually, others change little. These differences exist within populations and reflect variation in regulatory pathways. Again, the outcome is a spectrum, not a binary. When viewed this way, skin colour becomes less mysterious and less charged. It is simply one visible outcome of a system designed to balance competing demands under varying conditions. The gradient is the natural shape of that balance. This perspective also helps contextualize modern health issues. Vitamin D deficiency and UV-related skin damage occur across pigmentation levels because people now live far from ancestral environments. The gradient that once aligned reasonably well with sunlight exposure has been disrupted by indoor living, global migration, and artificial lighting. Biology has not had time to adjust. As a result, the relationship between skin colour and health is now situational rather than ancestral. People of all pigmentation levels must manage sun exposure and vitamin D intake based on current conditions, not inherited assumptions. The gradient remains, but its practical meaning has changed. Seeing skin colour as a gradient rather than a line dissolves many false questions. It removes the idea of beginnings and endpoints. It replaces, why did humans become white, with a more accurate question. How did humans adjust pigmentation gradually in response to changing light? The answer lies not in singular events, but in continuous variation shaped by environment, culture, and genetics. The gradient tells a story of connection rather than division, of shared mechanisms responding to different conditions, and of human variation that resists simple labels. Skin colour does not draw borders, it traces paths of movement, adaptation, and compromise under skies that change slowly as you walk beneath them. By the time humans began writing histories, building civilizations and passing stories down through generations, skin colour had already been shaped by tens of thousands of years of quiet adaptation. Biology had done its work long before language tried to explain it. But once humans began explaining the world to themselves, once stories hardened into beliefs and beliefs into systems, skin colour took on meanings it was never meant to carry. From that point on, myths grew around it, not because biology demanded them, but because societies did. One of the most persistent myths is that lighter skin represents something original, advanced, or closer to some imagined default human state. This idea collapses immediately under even minimal biological scrutiny. The earliest members of our species lived in Africa under intense sunlight and were dark-skinned. This is not speculation. It is supported by genetics, fossil evidence, and basic principles of evolution. Dark pigmentation is the ancestral human condition. Lighter pigmentation is a derived trait that emerged later, in multiple places, under specific environmental pressures. The notion that whiteness came first and darker skin followed is exactly backward. Another widespread misconception is that lighter skin spread because it conferred some kind of general superiority. This belief often hides behind vague language about adaptation, without specifying what was being adapted to. Lighter skin did not improve intelligence, creativity, strength, or morality. It did not enhance vision or endurance. It did one thing reasonably well in certain environments. It allowed more ultraviolet B radiation to penetrate the skin, supporting vitamin D synthesis when sunlight was scarce. That is the extent of its primary advantage. Outside of those conditions, that advantage disappears and can even become a liability. A related myth is that lighter skin is inherently more evolved. This misunderstanding comes from treating evolution as a ladder rather than a branching process. Evolution does not move toward perfection. It does not rank traits from primitive to advanced. It responds to local conditions. A trait that is advantageous in one environment can be neutral or harmful in another. Dark skin is not an evolutionary leftover. It remains highly adaptive in regions with intense sunlight. Lighter skin is not a destination. It is one solution among many to a specific set of constraints. There is also a persistent belief that skin colour differences correspond to deep genetic divisions between groups of people. This idea underpinned centuries of racial classification systems, many of which claimed scientific legitimacy. Modern genetics has dismantled these claims completely. The vast majority of human genetic variation exists within populations, not between them. Two people with very different skin tones may be more genetically similar to each other than two people with similar skin tones. Skin colour reflects a tiny subset of genetic variation, primarily related to how the body interacts with sunlight. It does not map neatly onto ancestry, capability, or any other complex trait. Another common myth is that skin colour defines biological races in any meaningful scientific sense. While the term race has social and historical significance, it does not correspond to discrete biological units. Human populations blend into one another gradually, just as skin colour does. There are no clear genetic boundaries where one race ends and another begins. Attempts to draw such lines rely on arbitrary criteria and ignore the continuous nature of human variation. Whiteness, in particular, is often treated as a singular, coherent biological category. In reality, it is not. Light skin in Northern Europe, light skin in East Asia, and light skin in some parts of Central Asia arose through different genetic pathways. They are not the same trait with the same history. Grouping them together under a single label obscures the independent evolutionary processes that produced them. Whiteness is a social category, not a biological one. Another deeply ingrained myth is that lighter skin is more natural or neutral, while darker skin is marked or specific. This perception is shaped by cultural dominance rather than biology. In many societies influenced by European colonialism, whiteness became the unmarked norm, the assumed default against which all other skin tones were measured. This framing has no biological basis. From an evolutionary perspective, all skin tones are equally specific, equally shaped by environment and history. There is also a misconception that skin colour is fixed and deterministic, that it defines what a person is capable of or suited for. Biology tells a different story. Skin pigmentation is flexible within limits. It responds to sunlight through tanning. It interacts with diet, lifestyle, and health. Its relevance changes depending on context. A skin tone that was adaptive in one environment may be mismatched in another. This does not reflect failure or deficiency. It reflects movement and change outpacing biology's ability to adjust. One particularly harmful myth is that lighter skin evolved because darker skin was somehow defective or problematic. This idea ignores the fact that dark pigmentation solved serious biological problems in high UV environments and continues to do so today. Dark skin provides effective protection against UV damage and folate degradation. It reduces the risk of certain skin cancers. It is not a burden. It is an adaptation with clear benefits under specific conditions. Another misconception treats skin colour as the primary or most important difference between human populations. In reality, it is one of the most superficial differences biologically. Traits like immune response, metabolism, disease resistance, and physiological adaptation to altitude or climate involve far more complex genetic variation and have had greater impact on survival. Skin colour stands out because it is visible, not because it is biologically central. Many myths about whiteness also stem from misunderstanding how fast evolution works. Some assume that lighter skin must have appeared recently and rapidly, perhaps tied to the rise of certain civilizations. In fact, skin lightening occurred over thousands of years, often long before the societies we associate with white populations existed. It was not driven by culture, intellect, or social organisation. It was driven by light. There is also a tendency to assume that skin colour differences are stable over time. History shows otherwise. Populations have shifted pigmentation through migration, mixing, and changing lifestyles. Ancient DNA studies have revealed that people living in Europe several thousand years ago often had darker skin than many modern Europeans. This does not mean they were fundamentally different. It means adaptation was ongoing. Another myth frames skin colour as a clear marker of geographic origin. While there is correlation between pigmentation and latitude, it is imperfect. Diet, altitude, cloud cover, and cultural practices all influence selective pressure. Two populations living at similar latitudes can have different skin tones due to differences in diet or climate. Conversely, populations at different latitudes can converge on similar pigmentation for different reasons. Geography alone does not dictate colour. Whiteness is also often mistakenly associated with vitamin D sufficiency in all contexts. In modern environments, this assumption can be dangerous. Lighter skin does not guarantee adequate vitamin D, especially in indoor lifestyles or polluted urban settings. Conversely, darker skin does not doom someone to deficiency if diet or supplementation compensates. The biological relationship between skin colour and vitamin D is conditional, not absolute. Some myths attempt to explain skin colour differences through moral or spiritual narratives, suggesting that pigmentation reflects virtue, purity, or divine favour. These stories arise from cultural traditions, not biology. They persist because they serve social purposes, often justifying inequality or dominance. Science offers no support for such interpretations. Another persistent misunderstanding is the idea that skin colour predicts behaviour or temperament. This belief has been used historically to stereotype and dehumanise. It has no biological basis. Skin pigmentation is regulated by melanocytes, responding to genetic and environmental cues. It does not influence personality, intelligence, or emotional capacity. It is also common to hear that lighter skin spread because it was preferred socially or sexually. While sexual selection can influence traits, there is little evidence that it played a primary role in the evolution of skin pigmentation. The timing and distribution of pigmentation changes align far more closely with environmental pressures than with universal aesthetic preferences. Moreover, standards of beauty vary widely across cultures and time periods, making it unlikely that a single preference drove global biological change. Another myth suggests that skin colour differences are ancient and immutable, as if they represent fixed divisions that have always existed. In reality, the most extreme pigmentation differences are relatively recent in evolutionary terms. For most of human history, variation was more limited. It expanded as humans dispersed into diverse environments and adopted new lifestyles. Understanding these myths requires recognizing how easily visible traits become symbols. Humans are pattern-seeking. We notice differences and assign meaning to them. Skin colour, being immediately visible, became a canvas onto which societies projected ideas about identity, worth, and belonging. These projections tell us far more about social history than about biology. When examined carefully, the biology of skin colour undermines every myth that tries to turn pigmentation into destiny. It shows a trait shaped by light, diet, and time, not by hierarchy or intention. It reveals shared mechanisms across all humans, adjusted locally rather than divided fundamentally. Dispelling these myths is not just an academic exercise. Misunderstandings about skin colour have real consequences, influencing healthcare, social policy, and interpersonal behaviour. Recognising skin colour as an adaptation rather than a marker of difference helps shift focus towards shared humanity and contextual understanding. Long after skin colour had finished responding to sunlight, long after melanin levels had been nudged up or down by geography and diet, humans began doing something new with those visible differences. they began telling stories about them. These stories did not emerge all at once, and they did not arise from biology itself. They grew slowly, shaped by culture, power, fear, and identity. Over time, skin colour stopped being just a biological trait and became a symbol, a shortcut for meaning, a surface onto which societies projected ideas about who belonged, who ruled, who laboured, and who mattered. To understand this shift, it helps to remember how recent it is. For the vast majority of human history, people lived in small groups with limited contact beyond neighbouring communities. Everyone around you looked broadly similar. Differences existed, but they were gradual and familiar. Skin colour did not divide humanity into categories because there was no global frame of reference. You did not compare yourself to distant populations you had never seen. Identity was shaped by kinship, language, shared work, and shared risk, not by pigmentation. As societies grew larger and more complex, that began to change. Agriculture allowed people to settle permanently. Settlements became cities. Trade networks expanded. People encountered others who looked, spoke, and lived differently. With those encounters came the human impulse to explain difference. Sometimes those explanations were neutral or curious. Sometimes they were fearful. Often they were tied to power. Culture, unlike biology, thrives on symbols. It takes visible traits and turns them into markers of identity. Skin colour, being immediately apparent, became one of those markers. It was easy to notice, easy to describe, easy to remember. And because it correlated loosely with geography, it could be woven into stories about origin and belonging. In many early societies, differences in skin tone were noted without moral judgment. Ancient texts from various civilizations describe people from different regions in observational terms. Darker skin was associated with hotter climates, lighter skin with colder ones. These descriptions did not initially imply hierarchy. They were attempts to make sense of the world's diversity. Over time, however, these observations became entangled with social structures. As empires expanded, conquest and enslavement became common features of human societies. Power differences demanded justification. Cultural narratives arose to explain why some groups ruled and others were ruled. Skin colour, already visible and associated with geography, became a convenient tool in these narratives. In many agrarian societies, lighter skin became associated with indoor labour and higher social status, while darker skin became associated with outdoor work. This association did not arise from biology but from class structure. Farmers, labourers and enslaved people worked under the sun. Elites did not. Over generations, this distinction hardened into an aesthetic preference, where lighter skin signalled wealth or leisure rather than ancestry. This pattern appeared in different forms across the world, including in societies with little contact with Europe. It shows that colour-based symbolism can arise independently when social hierarchies align with the environmental exposure. However, these systems were local and fluid. They did not claim universal biological meaning. That changed dramatically with the rise of European colonialism. As European powers expanded across the globe, they encountered populations with a wide range of skin tones. Colonial systems required ideological frameworks to justify domination, exploitation, and enslavement. Skin colour became central to those frameworks. European thinkers began to reinterpret visible differences through a distorted lens, transforming environmental adaptation into supposed evidence of inherent superiority or inferiority. Whiteness, already normalised within European societies, was elevated to a standard of humanity itself. Darkness was framed as deviation. This was not a scientific conclusion. It was a political and economic one. Pseudoscientific theories emerged to support these claims. Measurements of skulls, skin, and facial features were used to construct racial hierarchies. These efforts ignored the continuous nature of human variation and cherry-picked data to support predetermined conclusions. Biology was bent to serve ideology. Crucially, these racial categories were not discovered. They were invented. They reflected colonial power structures rather than natural divisions. The same populations could be classified differently depending on political context. Boundaries shifted, definitions changed. The categories themselves were unstable because they were never rooted in biology. Once established, these narratives fed back into culture. Laws, institutions, and social norms reinforced the idea that skin colour defined identity and worth. Over time, these ideas became internalised, shaping how people saw themselves and others. Culture transformed biology into destiny, even though biology had never implied such a thing. Identity became entangled with skin in ways that went far beyond adaptation. People were assigned roles, expectations, and limitations based on pigmentation. These assignments were justified through stories, myths, and selective interpretations of science. The original biological story, one of sunlight and survival, was buried beneath layers of meaning. It's important to recognise that these stories were not inevitable. They were choices made by societies under specific historical conditions. Different cultures have told different stories about skin colour. Some emphasised climate and environment, others emphasised class or spirituality. The idea that skin colour defines inherent human value is not universal. It is historically situated. Even within societies shaped by racial narratives, those narratives have shifted over time. Groups once excluded from the category of white in Europe and North America were later included as social boundaries changed. This fluidity exposes the artificial nature of the categories. Biology did not change. Stories did. Culture also shapes how individuals experience their own skin. Identity is not just assigned from outside. It is felt internally. People learn from a young age what their appearance is supposed to mean. These lessons influence self-perception, belonging, and opportunity. The psychological weight of skin colour comes from social interpretation, not from melanin itself. At the same time, culture can challenge and dismantle these stories. Scientific understanding of human variation has grown steadily. Genetics has revealed shared ancestry and overlapping variation. Anthropology has documented the social construction of race. History has traced the origins of racial ideologies. These insights provide tools for rewriting the narratives. However, cultural stories are resilient. They persist because they are embedded in institutions, habits, and assumptions. They are reinforced through media, education, and everyday interactions. Undoing them requires more than information. It requires sustained reflection and change. One of the most important distinctions to make is between identity and biology. Identity is shaped by culture, experience, and choice. Biology provides a starting point, not a script. Skin colour influences how others may perceive you, but it does not define who you are or what you are capable of. Confusing the two leads to reductionism and harm. Understanding the biological origins of skin colour does not erase cultural identity. It contextualises it. It shows that differences are not signs of separation but of shared adaptation under different conditions. It reframes diversity as variation within a single species rather than evidence of division. Culture, at its best, can hold complexity. It can tell stories that acknowledge difference without hierarchy. It can recognise history without freezing it into destiny. It can honour identity without mistaking symbols for substance. As modern societies become increasingly interconnected, the mismatch between ancient adaptations and contemporary meaning becomes more visible. People live far from ancestral environments. They carry skin tones shaped by one set of conditions into entirely different ones. Culture fills the explanatory gap, sometimes wisely, sometimes poorly. The challenge moving forward is not to deny skin colour, or pretend it does not matter socially. It does matter, because societies have made it matter. The challenge is to separate what skin colour actually represents biologically from what has been layered onto it culturally. Biologically, skin colour tells a simple story about light. Culturally, it has been made to tell stories about identity, power, and belonging. Those stories can change. They are not fixed by nature. When all the layers of explanation are peeled back, when biology has been separated from myth and culture disentangled from adaptation, what remains is a quieter question. Not why skin looks the way it does, and not how societies learn to divide themselves by it, but what skin colour actually tells us about being human. Not in a symbolic sense, and not as an identity imposed from the outside, but as a record of belonging written slowly into the body by movement, environment, and time. Human skin colour does not point inward toward difference as much as it points outward toward place. It is less a marker of who someone is than of where their ancestors lived and how they lived there. It reflects light levels, diets, climates, and daily routines repeated across generations. In that sense, skin colour is not about separation at all. It is about connection to geography, to sunlight, to shared biological constraints that every human body must negotiate. Belonging, at the biological level, has always been about fit rather than rank. Early humans belonged to environments not because they were superior to them, but because their bodies worked well enough within them. Skin pigmentation was part of that fit. Darker skin belonged in regions of intense sunlight because it protected folate and DNA. Lighter skin belonged in regions of weak sunlight because it supported vitamin D synthesis. Neither state was universal, neither was permanent, both were conditional. This conditional nature is important because it undermines the idea that skin colour encodes something essential or timeless about a person. It does not. It encodes a history of adaptation that may or may not align with present conditions. In a world where people move rapidly across continents and live under artificial lighting, the biological meaning of skin colour has become increasingly detached from daily life. Yet the cultural meanings assigned to it often remain rigid. Understanding skin colour as an adaptation reframes belonging in a fundamental way. It shifts the focus from categories to continuity, from boundaries to gradients, from identity as something fixed to identity as something layered and contextual. Skin colour tells a story of humans spreading, adjusting, and surviving in diverse environments, not of humans dividing into separate kinds. At a deeper level, skin colour reveals how little separates us biologically. The genes that influence pigmentation are a tiny fraction of the human genome. The mechanisms that produce melanin are shared across all populations. The differences lie in regulation, not in presence or absence. This means that the same biological system operates in every human, tuned slightly differently depending on ancestry and environment. Belonging, from this perspective, is not about sameness of appearance. It is about shared mechanisms responding to different conditions. The same solution, melanin, is adjusted rather than replaced. That continuity is the real signal of belonging, not the surface variation it produces. Another way to think about this is to consider how quickly skin colour can become irrelevant in biological terms. A person with dark ancestral pigmentation living in a low UV environment may experience vitamin D deficiency without dietary compensation. A person with light ancestral pigmentation living in a high UV environment may face increased risk of skin damage without protection. In both cases, the body is operating outside the conditions it adapted to. Biology does not recognize cultural categories, it responds to exposure. This mismatch highlights an uncomfortable truth. Skin color does not guarantee belonging in a biological sense. It does not ensure harmony with environment. It reflects a past that may no longer apply. Modern belonging, in biological terms, is often something that must be actively managed through diet, behaviour, and medical knowledge rather than inherited appearance. And yet, socially, skin colour continues to carry weight. People are read, judged, included, or excluded based on pigmentation long after its original biological meaning has faded. This disconnect between biological relevance and social significance is one of the defining tensions of modern human life. Understanding where skin colour came from does not erase that tension, but it does clarify it. It shows that the meanings attached to skin are not inevitable. They were built, and if they were built, they can be revised. Belonging, socially speaking, is always negotiated. It is shaped by shared language, shared values, shared experiences, and shared stories. Skin colour became one of those stories not because it had to, but because it was visible and convenient. It offered a shortcut for classification in societies that valued hierarchy and control. That shortcut persisted because it served interests, not because it reflected biology. When that history is acknowledged, skin colour loses its claim to authority. It becomes one trait among many, stripped of the burden it was never meant to carry. Belonging becomes something defined by participation rather than pigmentation. There is also a personal dimension to this. Individuals experience belonging not as an abstract concept, but as a feeling shaped by how they are treated and how they see themselves. Understanding the biological roots of skin colour can offer a kind of grounding. It can help people see their bodies not as symbols, but as outcomes of long-term adaptation, no more meaningful than eye shape or hair texture in terms of human worth. This understanding does not deny the reality of lived experience. Discrimination, privilege, and identity are real. They shape lives in concrete ways. But recognizing that these realities are layered on top of biology, rather than derived from it, opens space for change. It suggests that what feels permanent is not. Belonging, at its most basic, is about recognition, being seen as human. Biology supports this recognition by showing how shallow and flexible skin colour differences really are. Culture can either reinforce that recognition or undermine it. Another important insight emerges when we consider how quickly skin colour becomes ambiguous in mixed populations. Children of parents from different ancestral backgrounds often have pigmentation that does not fit neatly into categories. Their existence challenges rigid classification systems. Biology has always allowed for this blending. Culture struggles with it. This struggle reveals that skin colour categories are maintained through social effort rather than biological necessity. They require constant reinforcement through language, law, and habit. Without that reinforcement, the gradient reasserts itself, variation flows, boundaries blur. Seen this way, skin colour tells us that belonging has always been more fluid than fixed. Human populations have never been static. They have always moved, mixed, and adapted. Skin pigmentation records those movements imperfectly, leaving traces rather than clear labels. It also tells us something humbling about scale. The differences we emphasise socially are tiny compared to the similarities we share biologically. Every human skin cell operates on the same basic principles. Every human body manages the same trade-offs between protection and absorption, heat and cold, exposure and shelter. Skin colour is one visible outcome of that shared struggle, not evidence of separation. There is a tendency to search for final answers, for conclusions that settle questions once and for all. But the story of skin colour resists finality because it is ongoing. Human environments continue to change, lifestyles continue to shift, migration continues, culture evolves, biology follows, slowly, imperfectly, always catching up to a world that has already moved on. Belonging, then, is not something written permanently into the skin. It is negotiated in each generation, shaped by context rather than ancestry alone. Skin colour tells us where a story has been, not where it must go. If there is a lesson in this, it is a quiet one. Human differences are real, but they are shallow. Human connections are deep, but they are often overlooked. Skin colour, when understood biologically, points towards shared vulnerability and shared adaptation rather than division, and perhaps that is the most important thing it tells us, not who belongs where, but that belonging itself has never been about skin. It has always been about relationship, between bodies and environments, between people and places, between past conditions and present lives. The light that shaped human skin was never the same everywhere. It varied gradually, seasonally, unpredictably. Humans responded to it without knowing they were doing so. Culture came later and told stories about those responses, sometimes wisely, sometimes destructively. Understanding the difference between the two does not require agreement on identity or history. It only requires acknowledging what biology actually says and where it stops speaking. Skin color tells us that humans are adaptable, not divided. That variation emerges from movement, not separation. That visible differences often hide deep similarity. And that belonging, in its most fundamental sense, has always been broader than the categories we later built. And with that understanding, the story does not close. It simply continues, carried forward by bodies still adapting, cultures still telling stories, and humans still negotiating what it means to belong under light that keeps changing, slowly, quietly, without asking permission.